inflation, and the multiverse. Could our universe be just one of many, with inflationary phase spawning endless bubble universes? Friends, many of you are watching my videos without subscribing. Please subscribe to my channel. Thank you so much. The theory of cosmic inflation proposes a bizarre scenario where over the minuscule span of 1/1,000,000th of a trillionth of a second, shortly after the Big Bang, the entire infant universe expanded by a factor of at least 10 to the 26th power times its original size. This exponential growth spurt is hypothesized to have occurred due to the presence of a mysterious form of energy called inflation field permeating the primordial cosmos. As the inflation field decayed, it rapidly pushed apart all the matter and energy contained within, straightening ripples in the fabric of space-time to produce the flat, homogeneous universe we observe today. Without inflation, the observable universe simply would not look as it does. However, the heart of inflation theory resides not just in explaining large-scale patterns in our sky, but in its disruptive implication that our entire Hubble volume, all 100 billion galaxies within, is likely just one random bubble realm among endless others. According to the most widely accepted version of eternal inflation, each time inflation takes hold in a localized region, that patch of spacetime expands doubly exponentially, quickly blowing up to become many thousands of times larger than the already immense size it had reached before. Within this accelerated expansion phase, quantum fluctuations become magnified to astronomical proportions, seeding tiny density variations that will grow over billions of years into the galaxies and galactic clusters dotting our cosmic landscape. Crucially, inflationary expansion never fully ends. It merely gives way to slower, conventional cosmic expansion, punctuated by successive periods of accelerated swelling whenever potential inflation zones randomly activate within the wider cosmic fabric. As each inflationary region balloons upward, it fractures off into isolated spherical bubble universes, separated by vast empty voids. This fractal process repeats ad infinitum, recursively cascading down to smaller scales as new inflationary patches emerge within previously inflated zones, birthing their own daughters' universes endlessly. Thus, on the largest vistas, an eternally fractal cosmic structure would emerge, with more universes coming into being all the while as inflation persists forever. Our observable universe represents just one node within an infinite web of such exponentially proliferating bubble domains. All around you right now, and everywhere you have ever traveled spanning the known universe, are sheer nothingness, completely empty, dark, and extending to infinity, that separates your home bubble world from all the parallel realms populating this illimitable hyperspace of multiverses. Across those gulfs, inflation endlessly seeds new space-times that branch off from one original primordial inflation. The simplest interpretation envisions a single infinite spacetime manifold riddled through by bubble nucleation. More complex versions propose isolated megaverses of finite but unbounded regions not directly spatially continuous, but perhaps still communicating perturbations through stringy spacetime wormholes. Some theorize our universe's beginnings as just one tiny perturbation amidst the infinite turmoil of an eternally inflating steady state of distributed chaotic quantum fluctuation, birthing uncountably many universes without end. Whatever form inflation and the multiverse may take, it seems to many our cosmological picture has been forever altered, enlarging from a simple lone expanding cosmos to a fractal bubbleverse bubbling down to all scales of reality. Inflation generates not just spatial variation, but temporal diversity as well. Because each bubble zone inflates and splits off independently, and potentially at different rates depending on local conditions, it means that in one place the universal expansion may have proceeded twice as long as in another. Therefore, bubbles encompassing slower localized expansion histories would appear to observers inside them as much older than our apparent cosmic age of 13.7 million years. Some may even harbor life and civilizations far more evolved than our own, if located in zones where time has flowed much more extensively. In this light, a truly young universe from our provincial vantage may be a fallacy. Different inflating domains could range from newborn to age epochs far longer than time within the Hubble sphere. Multiple universes of varying temporal extent may even coexist simultaneously within a higher dimensional hyperspace. Moreover, the scalar inflaton field driving cosmic inflation is seen as analogous to the Higgs field, which endows elementary particles with mass. But since the Higgs strength could have had slightly different values in disconnected bubble domains, that might entail not just separate spacetime geometries, but diverse physical laws, with, for example, weaker or stronger nuclear forces. Thus, multiverses would stratify into diverging cosmic histories not only of space, but also of time and physics. The multiverse scenario takes the concept of cosmic fine-tuning to an extraordinary extreme. Our universe appears exquisitely well-adjusted to permit the emergence of complexity and life as we know it, with fundamental constants and strengths of forces holding values compatible for atoms, molecules, stars, and planets to form and coalesce. This has led many to speculate our cosmos parameters have been delicately pre-selected for or designed. However, in an inflating multiverse, each new bubble that buds off can potentially host any and all possible combinations of dimensionalities, forces, particles, and physical law parameters, as prescribed by the laws of quantum mechanics. It becomes much less remarkable than that by chance one bubble like ours arose with Goldilocks conditions for life. Statistically, wherever intelligent observers emerge to reflect on their cosmic habitat, they are certain to find its arrangement of quantum numbers conveniently tuned for their emergence. Otherwise, they simply would not be there to note the observation. In this picture, the multiverse resolves cosmological fine-tuning problems through probability. With an infinity of unseen domains, we are bound to inhabit one with life-friendly features solely by process of elimination. All conceivable universes exist somewhere, while we inevitably discover ourselves amidst the favorable fraction. Inflation and the multiverse thus provide a statistical anthropic rationale why our cosmic home appears so adapted to spawn life and intelligence. But an eternal inflationary multiverse faces steep challenges to be accepted as physical theory rather than just speculation. Most vexing perhaps is whether such a scenario can ever be tested or falsified through experiment or observation. Since different bubble realms are separated by a literal nothingness, interacting is impossible, leaving the multiverse metaphysically isolated from verification. Moreover, inflation on its own has yet to yield uniquely definitive predictions to account fully for fine details of the cosmic microwave background or large-scale structure. Finding evidence is also complicated because any multiverse signals imprinted on relic radiation from inflation occurred enormously early in cosmic history and thus processed through billions of years of galaxy evolution. New speculative ideas have been broached like cracking open wormholes to probe nearby bubble domains, detecting shadow matter transmitted between adjacent inflation zones, or measuring imprints of quantum multiverse interactions on spatial curvature. Some think signatures might remain of quantum fluctuations stretched to astrophysical scales if inflation commenced at an ultra-high energy scale close to where quantum gravity reigns. But observations remain well beyond existing technology and effects hard to disentangle from more conventional phenomena. Without evidence direct or indirect, the multiverse dwells for now in the realm of unfalsified metaphysics. Proving its physical reality remains illusory. Nevertheless, eternal inflation has become a foundation for much speculation regarding how the ultimate theory of everything incorporating quantum mechanics and gravity might appear once deciphered. According to some theorists, the multiverse is unavoidable from the vantage of string theory, the leading perspective on quantum spacetime. Within its framework, inflation appears to naturally arise from the dynamics of branes, higher dimensional membranes on which all known forces and particles hypothetically reside, colliding, annihilating, and seeding new universes without termination. Lensquake models of string theory posit a vast repository of possible vacuum states, with each representing a distinct set of dimension numbers, particle types, and force strengths. Eternal inflation punctuates this landscape as randomly tunneling domains continually sample new vacuum configurations, giving rise to diverse cosmic incarnations that evolve independently. Thus, at small brane collision scales lurking within wormholes, a theorized final theory may transparently manifest a multiverse structure. Realizing these models requires achieving a fully consistent quantum theory of gravity, far beyond present technical abilities. But the vision of ultimate laws inevitably embedding within themselves an infinite cosmic ecosystem of parallel universes is hard for many researchers to avoid. From our local planetary perch, any multiverse may seem too unfathomably gargantuan and remote to take seriously. Yet cutting-edge mathematics and physics continue pointing towards such an endless, perhaps even infinite, multi-level multiverse as an inescapable consequence once gravity and spacetime are wedded to quantum realities. Current evidence cannot disprove eternal inflation, and the hypothesis that our entire observable domain is but one bubble nucleus within a vastly larger metacosmos eternally seeded by primal quantum events. While skepticism remains prudent given hurdles to experimental test, the overall situation compels re-evaluating what universe truly means on a deeper level. Far more than mere speculation, cosmic inflation and a proliferating multiverse now constitute serious theoretical frameworks, shaping leading concepts in fundamental physics. Whether direct traces will emerge from future explorations of microworld or macrocosm is uncertain, but the larger implications for how our grandest scale picture of cosmos and reality itself may appear stir philosophical food for thought, inciting wonder anew at the strangeness and scale of creation unfolding all around, and perhaps within us. The Big Bang Theory is the prevailing cosmological model that describes the early development and subsequent evolution of the known universe. According to this scenario, around 13.7 billion years ago, the entire observed expanse of space, time, matter, and energy burst forth from an initial singularity. This was an infinitesimally dense point of infinite temperature, whose spectacular outward expansion initiated the formation and progression of physical processes that shaped the cosmos into the immense, grand structure observable today. From its earliest development in the 1920s by astronomer George Lemaitre, based on solutions to Einstein's gravitational field equations, to its confirmation as the best explanation for observed phenomena through crucial mid-century evidence, the Big Bang model has accumulated immense empirical validation over decades. Landmark verifications include the discovery of cosmic microwave background radiation, cosmic expansion of distant galaxies, and relative abundances of light atomic elements matching theoretical predictions from primordial nucleosynthesis in the first moments of the universe. Additional strong support has come through careful mapping of tiny temperature fluctuations in the leftover heat from the bang, matching patterns expected based on quantum fluctuations expanded to astronomical scales by a rapid early inflationary phase. The precise details involving the Big Bang singularity and first picosecons of cosmic history have not yet achieved a final theoretical formulation reconciling general relativity and quantum mechanics. Einstein's classical general relativity, which describes gravity and predicts spacetime warping, diverges at the immense densities implied for a single point of creation from which all realities spring forth. A fully consistent theory of quantum gravity is needed to describe spatiotemporal geometry at such Planck scale extremes. Nevertheless, within its first trillionth of a second, the entire observable mass-energy content of the modern universe is believed to have been compressed into an unthinkably hot, dense mass. Subatomic particles existed as a high-energy soup, with conditions resembling those found at the center of stars. A key prediction of the Big Bang model, which has gained tremendous observational backing, is that as the primordial fireball expanded and cooled, atomic nuclei, assembled from primordial hydrogen and helium gas, according to rules of nuclear fusion, enabled at progressively lower temperatures. About 370,000 years later, once temperatures dropped sufficiently, free electrons combined with atomic nuclei to form stable hydrogen and helium gas, initiating the process of recombination, which produced the first electrically neutral atoms. As the expanding, cooling universe grew less dense, individual atoms replaced the initial homogeneous plasma. Photons previously scattering off charged particles in plasma were at this point freed to stream freely through space, comprising relic thermal radiation from when the universe became transparent, visible today as the famous cosmic microwave background. Over the next several billion years, billions of generations of ancient stars lived and died, seeding heavier elements into the universe through stellar nucleosynthesis in successive cycles. Meanwhile, the uniform cosmic glow from primordial plasma gradually shifted toward longer infrared, visible and ultraviolet wavelengths as the unimaginably tiny quantum fluctuations visible in precision CMB maps were magnified across the sky by inflation and gravitational collapse into the large-scale structure observed today. Giant clusters of galaxies formed as mysterious dark matter, which makes up the bulk of matter in the universe, yet has never been directly observed, exerted its gravitational influence, steering visible matter into great cosmic filaments and voids across hundreds of millions of light years. The time when galaxies first emerge remains an active area of research, with current evidence pointing to early galaxies fully assembled not long after the epoch of cosmic reionization around 1 billion years post-Bang. Today's leading telescopes have revealed ancient galaxies dating back within 600 million years of inception, suggesting first-generation objects may have formed within the first few hundred million years, given limits on how soon after the Dark Age's ionizing luminosity could build up enough to reionize the universe. Improved future observatories may unveil galaxy assembly even closer to the Big Bang edge. What's clear is that over billions of years, countless titanic clusters conglomerated under mutual attraction across the expanding space fabric into the great galactic superclusters strung along immense dark matter filaments we inhabit today. Our home Milky Way galaxy harbored its own history, with hundreds of billions of stars generated over 10 billion years nested into galactic spiral arms and halo along with roving star clusters, and surrounded by a vast spherical arrangement of satellite dwarf galaxies and dark matter. 5 billion years ago, within a modest spiral arm of the Milky Way disk, our solar system coalesced from a giant collapsing molecular cloud, along with many other newly born star systems. As successive generations of planets formed from accretion of dust and gas orbiting the newborn sun, one world in the habitable outer asteroid belt developed stable temperatures and conditions suitable to harbor liquid water and complex organic molecules, the prerequisites for life. On the third planet, a thin, moving reservoir of biospheres quietly emerged into the blue African sky. Thus, across deep time, undirected yet lawful processes inherent to the fabric of reality itself unfolded from the simplest beginnings of the known cosmos. The ineffably hot, dense singularity of the Big Bang, a state beyond imagination, progressed through well-studied stages from primordial plasma to neutral hydrogen and helium gas, building across billions of years the astrophysical arena we today call home. An expansive visible universe beyond numbering, emergent from unthinkably extreme initial conditions. Though we may never observe back to the precise Planck epoch boundary with certainty, refined versions of inflation theory, and quantum gravity are helping illuminate what transmuted first nothingness into everything. Future instrumentation and breakthroughs may reveal closer views of those initial fractions of seconds, yielding fresh insights to complement and test theoretical models describing physics at the limits. Vital cosmological questions about dark matter and dark energy composition also motivate ongoing searches for new clues. But whatever ultimate revelations await, the unfolding grand narrative established by astrophysicists, constructing our best understanding of the ageless emergent cosmos since its beginning, remains one of the great achievements of human reason, a testament to science's ability to elucidate nature's deepest mysteries across the sweep of eons. Piece by piece, discoveries are illuminating how simple rules encoded at the foundations gave rise to complexity across scales unbounded, bringing forth the backdrop for life and intelligent life itself to one day contemplate the grandeur of the whole. In the late 1990s, one of the most surprising discoveries in the history of modern cosmology was made, which has had profound implications for our understanding of the universe. For decades, observations of distant galaxies had shown that the expansion of the universe was not slowing down under the attractive force of gravity, as had been the expected scenario based on known densities of matter. Instead, two independent research teams studying distant exploding stars called Type Ia supernovae obtained startling evidence that the rate of cosmic acceleration was actually accelerating, meaning some strange repulsive force was overriding gravity on the largest scales. This discovery of dark energy, demonstrating that roughly 68% of the total mass energy content of the observable universe consists of an unknown form of energy distributing itself homogeneously throughout empty space, has presented one of the greatest mysteries in physics ever since. The initial evidence was gathered using Type A supernova as bright, standardizable candles whose apparent brightness can be determined and used to calculate their distance from Earth. Because light traveling from more distant objects appears redder due to the cosmological redshift caused by expansion stretching its wavelength, measuring the redshift of faraway supernova can give their distance if their intrinsic luminosities are understood. In the late 1990s, the two teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the competing High-C Supernova Search Team, led by Brian Schmidt, independently tracked dozens of Type Ia supernova in distant galaxies up to several billion light-years away. After calibrating their luminosities based on closer supernova with more accurately measured distances, they were stunned to find the most remote supernova appeared intrinsically fainter than expected, implying the universe's rate of expansion has been gradually accelerating over billions of years, rather than slowing down as would be predicted in a universe dominated solely by normal matter and gravity. Their momentous 1998 papers, published back-to-back in the Astrophysical Journal, established dark energy as the dominant component driving space-time apart on cosmological scales. Since the initial discovery, many other independent lines of evidence have converged in strong agreement that dark energy makes up around 68.3% of all energy density in the universe today, according to Planck satellite measurements of cosmic microwave background anisotropies. Careful analyses combining multiple probes find the universe appears to have entered an accelerated expansion phase roughly 6 to 9 billion years ago. However, the physical nature of dark energy remains completely mysterious, with hundreds of theoretical models proposed but none proven. Dark energy's constant strength everywhere observed closely matches the theoretical value predicted for the vacuum energy density expected from a cosmological constant term in Einstein's field equations. Many proposals suspect dark energy may be a property of the quantum vacuum pervading space. However, quantum field theory calculations wildly overestimate its theoretical value, differing from the cosmological measurement by a factor of at least 10,120 in what is known as the worst theoretical prediction in modern physics. Resolving this immense discrepancy between theory and observation presents one of the deepest problems confronting the Planck-scale unification of quantum mechanics and gravity. Observational efforts to characterize dark energy properties are ongoing using multiple complementary techniques. The distribution of matter structures in the late universe is studied through large galaxy redshift surveys mapping filaments, walls and voids of galaxies across immense volumes reaching billions of light-years wide. Gravitational lensing analysis detects the subtle warping of light by intervening matter to probe underlying dark matter distributions that should correlate statistically with galaxies, while also directly weighing galaxy clusters. Peering further back to the first trillion years following the Big Bang, the cosmic microwave background anisotropy is visible in exquisite detail from satellites like WMAP and Planck are prized for tracing faint acoustic oscillations in the primordial plasma, which also leave imprints on late-time galaxy clustering that can distinguish dark energy models. Measuring baryon acoustic oscillation scale sizes across a range of redshifts extending to the epoch of matter radiation equality precisely tracks expansion history and fate of the universe. Careful monitoring of the changing apparent magnitudes of supernova, gamma-ray bursts, and other standard candle explosions across epochs seeks to detect deviations from a simple cosmological constant value with time. Ongoing and future sky surveys aim to capture billions of new objects, detecting subtle variations in growth of large-scale structure in hopes of unmasking dark energy as dynamical rather than steady in nature. While observational efforts seek to tighten constraints on dark energy behaviors, theorists speculate endlessly on its potential origins and properties. The cosmological constant remains a simple yet sufficiently accurate effective description observationally, but its deep vacuum energy value disagreement motivates proposals of dynamical scalar fields like quintessence evolving homogeneously in space, but changing in strength over the history of the cosmos. Cosmological alternatives raising new hypotheses include massive neutrinos, brane-world effects, extra dimensions, modifications to general relativity on cosmological scales, or exotic candidates like phantom dark energy with reverse gravitational properties. String theory and M-theory brane-world models envision our observable universe, confined to a 3D membrane floating within higher dimensions, with dark energy stemming from interaction between our brain and bulk gravitational degrees of freedom. Some study possible relationships between inflationary mechanisms responsible for seeding structure in the early cosmos and dark energy in the late universe, while others link dark energy to phase transitions and spontaneous symmetry breaking in the deep quantum vacuum possibly triggered by cosmological expansion itself. Various non-cosmological experiments probe dark energy from diverse angles. On microscopic scales, tests of general relativity using precision free fall or gravitational time delay measurements of pulsars or the orbital decay rate of binary systems search for anomalies which might arise from modifications to gravity on cosmological scales, masquerading as dark energy. Laboratory measurements and astrophysical neutrino observations attempt to constrain possible interactions between neutrinos and other particles that could affect neutrino masses and impact cosmological expansion, similar to a dynamical dark energy component. Underground detectors are seeking to directly detect theorized lightweight dark matter candidates, like actions, whose properties may relate to cosmological vacuum energy solutions. Several planned gravitational wave observatories aim to detect primordial gravitational waves from an inflationary epoch, potentially shedding light on early universe physics relevant for dark energy problems. Every new discovery relevant to unification, extra dimensions, quantum gravity, or acceleration of the universe provides clues to help decipher this deepest outstanding paradox in theoretical physics. Over 2 decades since its discovery, dark energy's nature remains one of the greatest unsolved frontiers in fundamental science. Any model seeking to describe physics at the interface of quantum mechanics and general relativity on cosmological scales must reconcile the immense discrepancy between dark energy's observed strength and theoretical vacuum energy predictions. Elucidating dynamical mechanisms which could naturally generate dark energy's properties consistent with cosmological and gravity tests poses a formidable challenge motivating a vast concurrent global effort across multiple complementary approaches. Cracking this mystery may profoundly revolutionize our conception of space, time, matter, and energy on the ultimate scale, achieving a deeper, harmonized theory of everything. Whether dark energy proves to be a cosmological constant, evolving quintessence, or something even more exotic and unexpected, its unveiling promises to uncover entirely new physics long sought yet still concealed within nature's depths. And with next-generation sky surveys and space observatories planned over the coming decades, we are embarking on humanity's most ambitious quest yet to finally unravel the greatest secret of our accelerating universe. An elegantly poetic yet profoundly challenging vision of reality emerges from string theory, the leading candidate for a theory of everything unifying all fundamental interactions. At its core, string theory proposes nature's basic constituents are infinitesimally tiny vibrating loops or strings rather than point-like particles, a simple tweak with mathematically beautiful yet hugely disruptive implications. For if elementary particles transmute into strings, whose behaviors are governed by principles of quantum mechanics and general relativity interwoven, it suggests our universe may actually have more expansive hidden dimensions beyond the familiar three of space and one of time perceived directly. According to string theory, at unimaginably minuscule Planck lengths, scales closer to a billionth of a trillionth of a trillionth of a meter, where strength of forces and properties of matter would have diverged from their known forms, the true nature of reality as vibrating strings within many additional curled-up dimensions becomes transparent. And perhaps most remarkably of all, mathematical consistency demands these extra dimensions must assume specific geometric shapes like minute Calabi-Yau manifolds or orbifolds. Resolving how such mind-bogglingly small topological features of unseen reality fold into our own cosmic arena has challenged physicists for decades. At these fundamental scales below even nuclear nuclei, strings would behave according to both quantum principles of Heisenberg uncertainty as well as Einstein's geometric theory of gravity formulated in general relativity, describing spacetime as a fabric worked by mass energy. Where quantum mechanics governs microscopic rules, while general relativity rules the macrocosmos, string theory is uniquely capable of seamlessly merging the two seemingly incompatible yet supremely valid descriptions. This arises because strings undergo quantum mechanical fluctuations as they vibrate, endowing them with resonant frequencies corresponding to different particle properties. Yet their motions are also governed by principles of curvature in higher dimensions, tying gravity intrinsically to strings' quantum behaviors. Strikingly, consistency of string interactions requires 10 dimensions for the anomalous behavior of particles at ultra-short distances predicted by quantum field theory to cancel out neatly. Some variants of string theory further hypothesize our familiar cosmos may be confined within a 3D membrane or brane floating within the higher dimensional bulk, analogous to a 2D sheet of paper within 3D space. Extra dimensions perpendicular to our brain would be invisible to everyday experience, yet gravitational couplings and certain quantum effects could leak into them with potential consequences detectable by future experiments. Whether through vibrating strings, bouncing brains, or other geometric formulations of quantum gravity, these theories provide mathematically self-consistent means to transcend general relativity and quantum mechanics incompatibility on microscopic scales. Achieving deep insights linking quantum descriptions of particles and forces with their emergent gravitic behaviors has been a profound victory, representing the pinnacle of scientific thought in theoretical physics to date. However, string theory also comes at a dear price theoretically, requiring a landscape of roughly 10,000 500 distinct vacuum configurations wherein fundamental constants and particle properties may randomly differ between separate bubble universes. Some of these diverse solutions could even harbor spaciotimes with unfamiliar numbers of dimensions, anisotropic cosmologies with directionally dependent forces, or violations of fundamental laws like unitarity and locality as known. The infamous string theory landscape implies observational truths within our universe represent just one random cosmic draw without preferred status. Some view this as a virtue, providing an explanation for the unexpected coincidences allowing life to arise. But to others it represents an untestable theoretical excess blurring predictive power. Much effort has focused on constructing explicit string vacuum matching properties of our universe, particularly candidate topological compactifications leading to realistic 4D spacetime with standard model particle content at low energies. Recent advances combining quantum field theoretic techniques with string geometries have made remarkable progress towards this goal. Specific orbifold and Calabi-U manifolds have even been engineered producing chiral fermions with 3 generations and recovering familiar forces Weinberg angles matching measurements, albeit not uniquely. Realistic astrophysical phenomenology has also emerged from certain brane models addressing dark matter composition and cosmological constant calibration. Yet uniquely falsifying predictions distinguishing string theory remain challenging given its vast landscape, necessitating alternative experimental approaches. One active avenue involves studying stringy quantum gravity imprints on cosmological processes like inflation and primordial gravitational waves, whose detection could offer unique windows to physics at or beyond Planck scales. Precision tests of general relativity using gravitational wave, lunar laser ranging, or pulsar timing also target possible low-energy relics from quantum gravity scenarios. Experimental searches for conjectured light, axionic, or axion-like dark matter candidates motivated from string moduli stabilization mechanisms constitute another indirect probe. Direct production of microscopic black holes, strings, or branes in high-energy particle collisions represents a tantalizing possibility some designs are sensitive to, in principle exposing fingerprints of quantum geometry. Whatever form verifications may eventually take, should nature conform to string theory's profound insights, marrying quantum structure and gravitic phenomena, it would profoundly reshape view of ultimate constituents and fabric of the universe. Remarkably, after over 4 decades of intense development, string theory remains mathematical physics' best hope of harmonizing quantum rules with Einstein's general relativity deep below nuclear scales. Through elegant geometric formulation of fundamental entities as tiny propagating strings rather than particles alone, consistent quantum theories of gravity emerge, naturally linking forces with dimensionality. Whether our cosmos truly arises from some particular string vacuum state, realizable at energy frontiers, or even represents just one random member of an infinity, only future experiments may reveal. But string theory has transformed views of reality's deepest constitution, advancing concepts that may yet fundamentally revise perceptions of quantum scales, spacetime, dimensionality, and provide gateways to test profoundly new regimes of nature. Though daunting challenges remain, it offers humanity's most logical route towards a theory of everything. While string theory has captured significant attention as a promising route towards quantum gravity, an alternative approach called loop quantum gravity also pursues the goal of unifying general relativity with quantum mechanics from a different perspective. Rather than focusing on particles as tiny vibrating strings, loop quantum gravity aims to quantize space and time directly using techniques from non-perturbative canonical quantum gravity. Developed in the 1980s by Carlo Rovelli, Alfei Ashtekar, and others, loop quantum gravity represents an ambitious program to fundamentally reformulate Einstein's gravitational theory as a quantum theory from the ground up. At the core of loop quantum gravity lies the realization that general relativity naturally describes space-time in terms of continuous geometry. However, as a quantum theory, space-time quantization requires its description in terms of discrete building blocks analogous to quantum harmonic oscillators or photons. Loop quantum gravity adopts a representation of the gravitational field in terms of loops and knots formed by elementary excitations called spin networks, which graphically depict discrete quantum states of geometry, just as an electromagnetic field can be described as discrete quanta-cold photons interacting along pathways. Loop quantum gravity aims to quantize continuous gravitational fields into discrete quantum chunks of intrinsic curvature knitted together through evolving spin network scaffolds. A breakthrough found space-time in loop quantum gravity emerges fundamentally as discrete or atomic at the smallest measurable scales near the Planck length. Properties like area and volume naturally arise only in quantized units, resembling an underlying discrete atomic structure to the very fabric of space-time itself. Remarkably, calculations show the minimum observable values for spatial areas and volumes in terms of the Planck units match precisely those deduced for black hole entropy calculations based on general relativity. Moreover, the discrete quantum geometry naturally resolves the divergences plaguing attempts to quantize gravity using traditional field-theoretic procedures. These successes suggest loop quantum gravity may address long-standing stumbling blocks to formulating a self-consistent quantum theory of space-time. At macroscopic scales, invisible discreteness averages out, matching Einstein's classical space-time predictions. Yet at ultra-high curvatures approaching singularities like the Big Bang, discrete geometries could leave observable traces. For example, loop quantum cosmology models find the Big Bang is replaced by a non-singular quantum bounce from a minimum volume when density reaches Planck scales. This avoids cosmological singularities resolved in canonical loop quantum gravity based on non-perturbative quantization. Other proposals suggest discreteness could resolve black hole information paradoxes through firework-type processes during final evaporation stages, yielding emergent unitarity. Advanced calculations are exploring consequences for astrophysical phenomena, inflationary universe models, and cosmological constant issues. Experimental guidance presents challenges, however. Though Planck-scale discreteness predictions could in principle leave signatures on cosmological fluctuations or gravitational wave spectra, these are beyond foreseeable detection. Some speculative ideas involve discrete geometry signatures on ultra-high energy cosmic rays or high-precision atomic interferometry sensitive to Planck scale modifications and violations of Lorentz invariance. But effects likely remain extremely small, requiring technology far beyond today's. More progress may come from symmetry-reduced toy models, lending insights on dynamical quantum geometry, matter-gravity interactions, and connections between spin networks and traditional space-time concepts. Overall, loop quantum gravity seeks to provide well-defined calculations avoiding infinities while seeding new intuition about quantum space-time structure. While promising approaches advancing, loop quantum gravity also faces difficult open questions. Current formulations work exclusively in vacuum and struggle including standard matter fields representation. Extending techniques to self-interacting fields coupling with quantum geometry pose formidable mathematical hurdles. Relating discrete spin network constructions directly to smooth macroscopic spacetime also lacks definitive understanding, though coarse-graining ideas show promise. Interpreting results and connecting formalism more directly with observation remains developmental. And despite intriguing connections noted, direct comparisons with higher dimensional string theory appear challenging given loop gravity's non-perturbative and intrinsically four-dimensional construction. Overall, loop quantum gravity pursues a radically different yet mathematically rigorous perspective on unifying gravity and quantum rules compared to string theory. Even if a complete realization of the program encounters obstacles, loop quantum gravity has stimulated invaluable new intuitions about quantizing space and time itself. Whether loop calculations, string vacua, alternative perspectives, or unforeseen possibilities ultimately crystallize at nature's deepest level remains an open frontier. But loop and related spin-foam models have shed light on consistent quantum geometric frameworks, merging general relativity with microscopic quantum behaviors in ways inspiring further progress. Addressing long-pursued dreams of a full theory of quantum gravity from diverse complementary angles promises breakthroughs transforming perspectives on ultimate limits of fundamental science. At the root of string theory's proposal that fundamental particles arise as tiny vibrating loops lies a specific hypothetical model known as the bosonic string, representing string theory's original and simplest incarnation, developed in the late 1960s. The bosonic string treats elementary particles not as point sources but rather as one-dimensional filaments distributed along circular or open linear paths, whose fluctuations determine their characteristics. Through appealing yet mathematically complex formalisms weaving together principles of quantum field theory, gravity, and geometry, insights from studying bosonic strings provided early glimpses of how microscopic vibrations within unseen higher dimensions might transmute into the diversity of observed atomic constituents and forces of nature. Within the bosonic string model, all elementary entities arise from common oscillatory modes of the underlying filamentary medium, differing solely based on their resonant frequency patterns. Just as different musical instruments produce distinct tones from fluctuations vibrating at favored wavelengths, so too might hadronic and leptonic particles emerge through quantized internal vibrations of supertony loops traversing unseen curled-up dimensions. Intriguingly, early analyses found bosonic string theory intrinsically incorporates gravitons, the proposed messenger particles carrying gravitational force, hinting at a deeper unity between fundamental interactions. However, consistency requirements forced strings to inhabit 26-dimensional spacetime for anomaly cancellation, far exceeding perceptions of our 4D universe. Subsequent decades of intense mathematical development lifted bosonic strings' profound yet abstract framework towards predictive physical theory. Refined descriptions incorporated fermionic degrees of freedom, extended string dynamics to curved spacetime regimes, and constructed scattering amplitudes to explore particle interactions and decays, finding promising matches to hadron masses and other measured data. Nevertheless, difficulties emerged, with tachyon modes signaling intrinsic instabilities and absence of chiral spin 1 fermions representing our material world. Though unveiling strings' intrinsic unity of forces and discreteness of quantum spacetime, serious shortcomings established the original bosonic formulation could only represent a preliminary scaffolding for a true theory of everything. Remarkably, 1980 advances uncovered how attaching additional supersymmetric structures to bosonic strings resolved key failures while retaining key virtues. Graded by 16 components belonging to different representations of spacetime supersymmetry groups, strings' internal fluctuations incorporate fermionic oscillation modes on equal dynamical footing with bosons. This superstring revolution spurred a flurry of activity transforming disconnected mathematical curiosities into a consistent quantum framework describing gravity and matter as vibrating strands, achieving full cancellation between fermionic and bosonic anomalies, permitting a physically preferable 10-dimensional target space. Today's leading formulations of superstring theory have expanded the canvas of theoretical possibilities far beyond bosonic antecedents. Yet bosonic strings retain great historical significance as the original conceptual seed and progenitor of mathematical formalism, driving initial insights into strings as fundamental entities. Its anomaly cancellation conditions guided pathways to supersymmetric extensions unifying all interactions, while early scattering amplitudes directly motivated phenomena from brains in M-theory. Though long superseded as an ultimate physical model, bosonic strings established first principles, still guiding string theory's modern incarnations at frontiers, where quantum gravity dominates over familiar spacetime conceptions. They demonstrated how hypothesizing quanta of closed loops offers logically consistent schemes to describe fundamental interactions throughout nature that may one day illuminate ultimate limits of energy, matter, and reality itself. The bosonic string hypothesis pictures elementary particles arising from one-dimensional oscillating loops circling within unobserved higher dimensions, differing solely based on resonant vibrational modes. Early pioneering analyses established bosonic strings intrinsically incorporate consistent quantum descriptions of gravity, while identifying full particle spectra. However, various inconsistencies ultimately motivated descendants incorporating supersymmetric modifications, resolving issues like tachyonic instabilities, and allowed realistic 10D target spaces. Although no longer pursued as a physical theory in isolation, bosonic strings played an indispensable role historically as string theory's conceptual origin, laying mathematical and conceptual groundwork, stimulating insights guiding modern formulations. They demonstrated hypothesizing fundamental spacetime quanta as closed strings provides logically consistent frameworks addressing long-sought unification dreams, holding promise to revolutionize views of physics' outer boundaries. In string theory's formative stages, bosonic strings represented the prototypical model examining elementary particles as loops vibrating within hidden curl-up dimensions. Initial studies found bosonic strings arise from common vibrational modes along circular or linear filaments, with gravitational interactions emerging intrinsically from quantum fluctuations. Anomaly cancellation conditions directed towards spacetime supersymmetry resolutions, establishing bosonic strings historically as the conceptual seeds driving superstring descendants. While inconsistent as an ultimate theory, bosonic strings mathematics framed early insights motivating modern formulations at frontiers, marrying quantum mechanics and gravity. They demonstrated hypothesizing quantized closed strings provides logically consistent means to describe nature's deepest constituents and merger of fundamental forces, holding promise today to profoundly revise perspectives on ultimate limits of matter, energy, and reality itself. Early bosonic string models treated all particles as arising from distinct vibrational modes of fundamentally identical circular or linear filamentary quanta distributed along unseen extra dimensions. However, inconsistencies required successors incorporating fermionic degrees of freedom and supersymmetric modifications to reconcile chiral fermions, anomaly cancellations, and realistic 10D theories. But historically bosonic strings played an indispensable pioneering role, framing string theory's underlying conception of elementary particles as tiny vibrating strings. Their mathematical frames stimulated seminal insights guiding modern formulations, uniting quantum principles with gravity's geometry. Although long superseded, bosonic strings' legacy demonstrates hypothesizing spacetime's quantized structure as closed strings establishes logically self-consistent frameworks, holding promise to revolutionize views of physics' farthest reaches. One of the most profound implications of the cosmic inflation paradigm is the speculation it may persist endlessly throughout the cosmos, fractally seeding new pocket universes without termination. According to the eternal inflation scenario, each time the rapid expansion driven by the inflaton field becomes reactivated within some localized region of spacetime, an exponentially swelling bubble universe spots off, and within this bubble additional nested inflationary regions can emerge to recursively seed daughter domains forever. This pictures inflation proceeding ad infinitum throughout the emergent multiverse, sequentially nucleating bubble realms disconnected from yet in parallel with our own expanding visible region. The extraordinary scale of such an eternally fractal cosmic structure challenges conventional perspective and is hotly debated, yet its implications motivate rethinking the global context enveloping our known universe. Within eternal inflation, while the overall scale factor of the universe grows according to classical expansion, each local inflationary bubble experiences doubly exponential acceleration as quantum fluctuations are magnified to astronomical wavelengths. This continues until scalar field gradients smooth away, terminating localized inflation, but leaving residual potential to reignite randomly nearby. Crucially though, even as inflation ends in any region, new zones can still initiate endlessly, preserving inflation globally forever. Some conceptualize the multiverse structure as a texture whose fundamental constituents are isolated bubble universes, pinching off from this continuous process, while others argue inflationary domains endure as open-ended semi-classical entities embedded within an unbounded inflationary spacetime. Either way, eternal inflation's recursive fragmentation endlessly seeds disconnected bubble pocket universes, randomly sampling all possibilities prescribed by a string landscape of vacuum configurations, realizing different forces, constants, and even dimensionalities. This proliferating cosmic ecosystem implies inflation, and by extension the universe, has no meaningful beginning in time, existing eternally in a scale-invariant steady state. Proponents argue eternal inflation resolves philosophical problems involving absolute origins, while providing a predictive statistical framework reflecting our universe as typical rather than finely tuned. Skeptics counter speculative scenarios remain difficult, if not impossible to test, and lack clear cosmological signatures distinguishing hypotheses. Modeling intricate interactions within an eternal multiverse rigorously presents immense technical challenges, but some proposals emerge. Slow roll approximations highlight key parameters controlling inflation's longevity, while stochastic formalisms statistically sample evolution of scalar fields driving eternal bifurcation. Bubble domain interactions may leave imprints like topological defects at domain junctions, cosmological constant variations, gravitational wave backgrounds from spatial curvature mismatches, or quantum multiverse correlations detectable on CMB scales. Early bubble collision processes have also been proposed as a resolution to black hole information problems. However, most predictions resemble those from temporary inflation models lacking smoking guns. Probing eternal inflation's vast, causally separate landscape mathematically and observationally remains an enormous open problem. While eternal inflation catalyzes profound shifts, reconsidering inflation's global aftermath, controversy surrounds interpretations, and empirically distinguishing between scenarios remains a profound barrier. Even if consistent theoretical treatments crystallize, verifying inflation's literal infinity empirically could elude any scientific perspective. So question marks linger over eternal inflation's theoretical appeal versus observational accessibility. Is it an idea stimulating insights but destined to remain metaphysical? Or could advancing cosmology someday detect multiple bubble domain walls or even enter new vacuum epochs? Whatever form conclusive resolutions take, eternal inflation exemplifies how inflationary thinking continues pushing cosmological perspectives to new domains, addressing deep questions concerning nature's ultimate structure and boundaries. The eternal inflation paradigm follows cosmic inflation's logical extension, whereby accelerated expansion, driven by scalar fields, never fully terminates, enabling endlessly iterative fractal structure formation across scales. Under eternal inflation, each emergence of localized accelerated stretching spawns an exponentially swelling isolated bubble universe, yet inflation persists globally as new zones continuously activate. This pictures an eternally self-reproducing inflationary multiverse where our Hubble volume represents just one ephemeral region within a scale-free inflationary steady state. While theoretical refinements develop and distinguishing empirical predictions remain challenging, eternal inflation motivates radically re-envisioning inflation cosmology's global aftermath and context for where our universe sits within the cosmos' overarching patterns and evolution. Regardless outcomes, eternal inflation stimulates profoundly impactful shifts in cosmological perspective toward nature's deepest principles. One of the most ambitious unified theories speculating on the ultimate fate and origins of the cosmos comes from eminent mathematical physicist Sir Roger Penrose in his conception of conformal cyclic cosmology. Based on marrying general relativity with quantum mechanics through the lens of Weyl curvature geometry, CCC proposes our observable universe represents merely one aeon within an endless cyclic succession, where each vast expansion phase gives way to a cataclysmic collapse, seeding the next genesis. If correct, CCC implies past and future universally bounce into one another through conformal mapping, blurring divisions between cosmology and ultimate destiny in a cosmography far more elaborate than even inflationary multiverse scenarios. In CCC, general relativity's description of spacetime curvature informs quantum reality everywhere through Weyl curvature quantities, which remain finite even at singular endpoints of spacetimes. As the universe approaches ultimate contraction according to classical theory, Weyl curvature and associated scalar products blow up scale invariantly, forming conformal singularities distinct from traditional singularities. When gravitational attraction overwhelms expansion around 100 billion years hence in our aeon, based on LCDM, immense black holes will merge relentlessly, ejecting deep space photons containing imprints of late universe, structure and effects encoding nature's deepest laws. Extreme collision morphs curving spacetime within each black hole into a white hole pure radiance burst, expanding a new aeon throughout reborn empty space. Quantum gravity effects smear out discreteness to transform singular white hole flash into smooth initial LCDM expansion phase, closing the cyclic loop. Crucially, CCC foundations rest on Bekenstein-Hawking entropy area theorems, demonstrating black holes store finite thermodynamic information through event horizon geometry alone. As contracted aeons drain into black singularities, their macro-state boundary information must survive into the emergent white hole rebirth, where quantum coherence rapidly reconstitutes classical spacetime patterns. Spin networks entangled globally encode primordial memory templates, sustaining repetitions. Thus, cosmic cyclicity flows inevitably from general relativistic and quantum-based principles without tuning. Each aeon's ultimate fate dissolves into an aeon prior through scale-invariant conformal folding, with expansion inexorably recycling toward contraction's moment of renewal. Across boundless becoming, physical constants, forces and space-time arena recycle eternally through unbroken cyclic self-gradation. CCC makes several testable predictions which could corroborate its elegant resolution of cosmological ultimate destiny. Most directly, gravitational memory effects imprinted within each collapse onto white holes' rebirth should polarize background radiation directionally between aeons according to special conformal transformations. Fine structure in next aeon CMB will subtend repeating patterns from its predecessor's late-period black hole collisions. Advanced gravitational wave observatories may detect primordial fossil waves breaching aeons reverberated through cycles. Dark energy scales as LCDM approaches L equals 0 singularity. Also subtle quantum gravity violations on cosmological scales and variations in observable constants could lend support. However, conforming predictions and truly discriminating CCC remain enormous empirical challenges far beyond present technology. Regardless outcomes, CCC stimulates profound shifts re-envisioning cosmology's deepest structures and nature. CCC's speculation that general relativity and quantum mechanics inevitably weave cosmic becoming into unending cyclicity through scale-invariant conformal mapping recasts perspectives on ultimate cosmic fates and primordial origins. Each grand universal expansion phase recycles conformally into contractions, seeding daughter domains in self-perpetuating succession. Subtle quantum links encode memories propagating through singular collapses, sustaining repetitions. While experimental validation faces immense difficulties, CCC exemplifies theoretical cosmology's potential to fundamentally redefine perspectives on ultimate cosmic structures and processes at staggering scales far surpassing inflationary paradigms. Even if empirical confirmation eludes present scope, CCC stimulates seminal ideas transcending past cosmological borders through profound unity of general relativity, quantum principles, and persistent cosmic becoming on levels dwarfing mundane horizons. Its visionary scope may yet offer profound insights into physical destiny's deepest nature. Penrose's conformal cyclic cosmology unites general relativity and quantum mechanics through Weyl curvature geometry at unparalleled cosmological scales. Each grand aeon of universal expansion throughout 100 of billions of years conformally collapses under gravity into black singularities. Their mergers transmit late structure through entangled spin networks, polarizing white hole rebirths, seeding new accelerating phases. Subtle quantum links encode each aeon prior, sustaining conformal recycling perpetually. While observational verification faces immense technical difficulty, CCC predicts gravitational memory-bridging aeons could leave subtle CMB sky polarization signals as prime signature. Regardless outcomes, CCC exemplifies theoretical cosmology's potential to fundamentally redefine cosmic parameters. Its visionary conceptions may offer profound intuitions into ultimate physical destiny far beyond mundane perceptions, even if validation eludes present experimental scope. Stimulates seminal shifts rethinking cosmic structures across nature's grandest domains. Conformal cyclic cosmology proposes the repeated conformal self-collapse and re-emergence of cyclical universal aeons through infinite cyclic self-creation, motivated by general relativity and quantum principles at the ultimate cosmological scale. Each grand expansion phase conformally falls under gravity into black singular mergers whose entangled spin network encodings transmit late structure subtly imprinting white hole rebirths of fresh aeons. Subtle quantum links sustain cosmological memory across cyclic phases predicted observable through polarization fossils between cosmic eras. Although observational corroboration presents immense technical obstacles far exceeding present scope, CCC exemplifies theoretical cosmology's capacity to fundamentally redefine perspectives on cosmic processes across nature's deepest scales. Its profound intuitions stimulate seminal shifts envisioning physical destiny's furthest frontier, with vision to offer insights beyond mundane horizons. Our blue planet Earth has borne witness to untold catastrophes across its billion-year history that have deeply impacted the biosphere and evolution of complex organisms inhabiting its diverse niches. From colliding continents and erupting volcanoes to shifting ice ages and surging sea levels, intermittent natural disasters have punctuated otherwise stable periods, enabling radical innovations, yet also triggering wholesale die-offs. Among the most physically destructive events with potential to reshape entire climates and ecological assemblages were immense asteroid impacts, hypothesized to hold dramatic importance, molding the course of terrestrial life across deep time. Intriguing clues suggest several massive collisions may have reset environmental conditions worldwide, opening pathways for new phylogenetic radiations after mass extinctions cleared the field. Understanding roles of such intermittent asteroid bombardments offers insight into serendipitous forces sculpting the biosphere's emergent complexity across thresholds of regeneration after cataclysms. Perhaps the most famous suspect impact associated with the major species turnover occurred 66 million years ago at the boundary of the Cretaceous and Paleogene periods, wiping out non-avian dinosaurs together with approximately 75% of plant and animal species inhabiting the world during Earth's Mesozoic era. Discovery of the 180-kilometer wide Chicxulub impact crater buried underground in Mexico's Yucatan Peninsula provided smoking gun evidence validating the so-called Alvarez hypothesis launched in 1980 linking this mass extinction event to a cosmic collision. Global effects from the impact, including atmospheric dust veiling the sun for years and immense firestorms ignited across 4 seasons, are implicated in devastating ecological fallout, overturning dominant ecological regimes intact for over 100 million years prior. Recoveries began within a few 100,000 years as niches emptied amidst climatic upheavals opened new avenues for mammalian ascents and avian diversifications among survivors. Even more ancient impacts may have just as profoundly redirected evolutionary pathways en route to Mesozoic emergences. Around 265 million years ago, toward the close of the Permian period, approximately 95% of marine and 70% terrestrial species perished in what's considered Earth's most severe mass extinction. One leading proposal connects the so-called Great Dying with environmental perturbations wrought by the Manicouagan impact, leaving a colossal 215-kilometer basin buried under northern Quebec, Canada. Blast effects and global atmospheric changes unleashed by an impactor that size could easily account for toxic conditions worldwide, eliminating highly sensitive taxa while priming Phanerozoic ecosystems remodeling. Some evidence suggests recovery commencing around 8 million years post-impact saw explosive radiations of archosaurs and early mammals feeling ecological release as Triassic dawned afresh. Journeying further back 850 million years ago, near the close of the Neoproterozoic era, marks an enigmatic interval dubbed the Boring Billion for seeming stasis in animal evolutions reaching simple Ediacaran biotas with Cambrian explosion complexities. However, geologic fingerprints indicate multiple significant extraterrestrial impacts may have paced environmental fluctuations during this understudied epoch, shaping contingencies enabling Mesozoic emergences. The vast 1,080-kilometer Vredefort crater in South Africa provides smoking gun for one planetary collision, dated to 2 billion years ago during the Paleoproterozoic, coinciding with snowball Earth glaciations potentially linked to global climate upheavals and aftermath biological innovations. Earlier yet, the heavily eroded Sudbury Structure Impact Basin near Lake Huron, encapsulating a 1,880-kilometer crater, may correlate within error bars to another hypothesized impact 2.5 billion years ago during late Paleoproterozoic, near suggested great oxidation event when atmospheric oxygen concentrations rose profoundly. Both timing and scale of these impacts could match proposed triggers for severe ecological transitions, opening doors to oxygenation, multicellularity, and early complexity gains across Precambrian aeons before Phanerozoic proliferation. Most recently, Earth encountered impacts from objects as large as 5 to 10 kilometers around 11,000 years ago during the Younger Dryas interval, marking abrupt return to Ice Age conditions after fleeting warm period around 12,800 years ago. Multiple impact markers have been recovered globally at this proposed boundary, including platinum anomalies, carbon spherule layers, and milk-glass or microspherule deposits interpreted by some as debris from several airbursts or low-angle strikes from fragmented comets or disintegrating planetary bodies. Ensuing environmental changes have been implicated as possible catalysts for Pleistocene megafaunal extinctions, including mammoths and Clovis peoples, while Neolithic cultures rose. Much ongoing research debates various extraterrestrial causes, with climate transitions from melting ice sheets alone. But the scale of short-term Younger Dryas global cooling together with impact evidence continues driving hypotheses of humanity near brush with comet-driven catastrophe, ushering abrupt ecological turnover before warming's resumption. Amid ongoing refinements of dating, proxy records, and impact modeling efforts, evidence mounts steady asteroid or comet bombardments, punctuated intervals where atmospheric perturbations cascaded into wide-scale biotic crises. Mass extinctions open release for opportunistic radiations as conditions stabilized anew, contributing to the biosphere incremental growth in complexification across unfathomable deep time. Remarkably, had any of Earth's largest impactors missed or arrived a few million years earlier or later, alternative evolutionary pathways may have eventuated through contingency. As anthropic pressures now threaten global stability, examining past asteroid strikes' influence on climate change and biotic turnover offers perspective on tipping points where comparatively modest forcing unleashed nonlinear dynamics across living systems. Untangling asteroid impacts, deep history roles holds lessons for biodiversity's future resilience in the Anthropocene under humanity's ongoing transformation of the planet today. Dating back through Earth's 4.6 billion year history, recurring impacts from objects over 10 kilometers likely punctuated many crucial transitions in the biosphere's development and turnover throughout the Precambrian and Phanerozoic eras. Whether sparking explosive diversifications after mass die-offs cleared terrain, resetting atmospheric chemistry, enabling new metabolisms, or driving climatic fluctuations patterning Phanerozoic provincially based on geographic bouncebacks, intermittent asteroid strikes appear intertwined with contingencies giving rise to complexity across deep time. Evidence mounts they played underappreciated roles shaping evolutionary pathways and contingencies culminating in humanity's emergence at the apex of post-extinction recoveries in the fragile Quaternary. As anthropic pressures now threaten global stability, examining past asteroid impacts' influence offers perspective on ecological resilience and our precarious place within nature's deep history across the vast cosmological scales sculpting terrestrial life. Few forces rivaled immense asteroid impacts in potentially resetting biosphere and environmental conditions on a global scale throughout Earth's history, with clues suggesting several strikes coincided with or contributed to major mass extinction events. Whether igniting short-term crises eliminated taxa or initiating long-term changes enabling new radiation opportunities, intermittent asteroid bombardments seem profoundly intertwined with contingencies unfolding complexity across deep time. Evidence is steadily amassing they sculpted evolutionary pathways and geological transitions pivotal for multicellular ascendance, while also punctuating dominance and turnover of many taxonomic kingdoms populating diverse Phanerozoic biomes. Examining their intermittent roles offers fresh perspective on biotic resilience and fragility within nature deep time processes unfolding across vaster cosmological scales that birthed and shaped terrestrial life. Catastrophic asteroid impacts appear intertwined with contingencies unfolding the biosphere's development, turnover, and complexification across Earth's deep history and precarious Anthropocene present. Dating back billions of years, recurrent strikes punctuated crucial transitions and mass extinctions where atmospheric and environmental changes cascaded into biotic crises and recoveries. Evidence suggests several key impacts coincided with or enabled revolutions like Great Oxidation, multicellular emergences, and Phanerozoic diversifications thereafter. Most recently near humanity's dawn, younger Dryas events may have ushered Pleistocene turnover preceding Neolithic ascents. Throughout, intermittent asteroid bombardments seem profoundly intertwined with geological and evolutionary contingencies realized across unfathomable stretches of time. Their intermittent roles offer fresh perspectives on ecological fragility within deep cosmological processes vital for life, and humanity's responsibilities amid unprecedented global changes today. Over billions of years, our planet bore witness through its lithic archives to recurrent asteroid or comet impacts capable of instantly resetting global environmental baselines by igniting widespread biome-transforming climate instabilities. Not only did immense strikes likely eliminate dominant species at scales shaking mass extinctions, but evidence suggests several may have uniquely enabled subsequent radiations and contingencies epitomizing life's incremental ascent throughout deep time. Their forgotten yet recurring roles appear profoundly intertwined with evolutionary pathways and contingencies realized since microbes first emerged under favorable yet volatile terrestrial conditions. As anthropogenic destabilizations now threaten biospheric homeostasis on which humankind ultimately depends, appreciating life's fragile yet resilient interweaving within nature's deep history offers timely perspective on humanity's responsibilities amid transformations of the living world still unfolding today across vast cosmological domains beyond narrow perception. Conventional wisdom frames gravity as a fundamental force governed by Einstein's general relativity, warping the very fabric of spacetime according to mass-energy distributions. However, some physicists speculate gravity may instead represent an effective description of deeper phenomena where the illusion of spacetime curvature emerges from larger-scale behaviors of quantum entanglements below. Dubbed emergent or entropic gravity proposals, these ideas suggest that rather than gravity driving dynamics, dynamics themselves conspire to give rise to an apparent gravitational force as a collective side effect. Some emergent gravity schemes even purport to explain enigmatic dark matter as an emergent feature stemming from quantum substructure. If validated, emergent perspectives could profoundly recast understanding of reality to deepest operational principles. Pioneering work by Jacobson in the 1990 linked Einstein field equations depicting space-time geometry to thermodynamic laws governing black hole entropy. By associating entropy with causal horizon surface area, as per Bekenstein-Hawking, gravity's curvature can be derived from entropy maximization principles applied locally to Rindler causal horizons. This inspired entropic force scenarios, postulating spacetime geometry arises as an entropy gradient between vacuum fluctuations within and beyond a horizon. Gravity emerges from thermodynamic behavior at ultramicroscopic scales rather than existing fundamentally. Analogous to macroscopic forces arising from microscopic interactions, gravity would represent an emergent large-scale collective effect. Further developments introduced atomic description of spacetime based on discrete quantum geometries from loop quantum gravity and spin network models. Gravitational interactions between quanta were proposed emergent from Wheeler-DeWitt conformal constraints between quantum bits demarcating causal diamonds. Gravitons were reconceptualized as quasi-particle excitations of quantum geometry rather than fundamental messenger quanta. Similar ideas reformulate general relativity using condensed matter-inspired techniques, depicting smoothly curved manifolds as coarse-grained emergent effective behaviors from deeper-level discrete matter-energy complexes. Quantum entanglement between atoms of spacetime replace gravitons as primitives, with curvature emerging as an entanglement byproduct. Dark matter too could stem from deeper-level quantum characteristics according to some emergent gravity speculations. One proposal invokes condensed matter analogs of topological defect textures emerging in continuous quantum fields as dark matter signatures. Extended technicolor models portray dark matter arising through quark condensation due to rich hidden sector dynamics. Variable gravity schemes propose large gravitational constant fluctuations mediating cold dark matter effects as the manifestation of spacetime quasi-particle excitations within quantum foam. Certain pre-geometry frameworks depict dark matter as a manifestation of symmetry-breaking transitions from subplankian pre-geometry into the spatiotemporal arena. Remarkably, emergent perspectives provide alternative interpretations not requiring fundamental dark matter constituents, resolving apparent fine-tuning issues. Connecting speculative ideas with experimental guidance presents immense challenges. However, efforts seek fingerprints of deeper-level quantum structure on cosmological distributions and galaxy rotation curves. Improved tests of cosmological and gravitational consistency relations aim to trap signatures of parametric quantum subprocesses contributing dark energy and dark matter impressions. Precision probes of Lamb shifts, Hawking radiation, and gravitational lensing might unveil clues betraying spacetime's non-fundamental nature. Quantum gravity-inspired modifications to dispersion relations or vacuum polarization effects could become observable with advancing capabilities exploring cosmological frontiers and primordial epochs. Though establishing emergent principles conclusively will demand revolutionizing current observational reach, speculations continue motivating new ways of glimpsing cosmos' deepest operational machinery. Whether Einstein's geometric picture endures or gravity one day proves an illusion emanating from coarser-scale quantum fabrics, emergent perspectives disrupt prior conceptions. They instill profound revisions reimagining core categories of matter, energy, and even notion of continuous space-time as theoretically derived from deeper Planck-scale textures. Remarkably, emergent scenarios address dark matter's composition while opening fresh perspectives on ultimate physical principles. Regardless outcomes, they disrupt complacency by instilling our most basic cosmological suppositions as candidate emergent effective descriptions rather than fundamental assumptions. Considering gravity and dark matter as derivative collective properties stimulates breakthrough ways of glimpsing inner constitution veiled beyond observables. Though theoretical challenges remain immense, emergent concepts invigorate, exploring beyond prior observational frontiers toward nature's deepest foundations. Tracing developments since Jacobson's foundational work applying thermodynamic and holographic principles to derive Einstein's field equations from deep-level conformal degrees of freedom, emergence concepts substantively broadened. Loop quantum gravity discretizations, spin network insights and analogy to condensed matter topology furnished new perspectives depicting smoothly curved spacetime and traversable wormholes as derived from deeper-level quantum fabrics. Entropic forces, pre-geometry and Wheeler-DeWitt conformal constraints supplied variant mathematical frameworks reconceptualizing gravity as quasi-particle excitations arising from quantum geometric textures rather than fundamental interactions. Dark matter interpretations invoked condensed topological defects or hidden sector quantum condensates, resolving its composition mysteries. Progress inspires reimagining established categories as theoretically emergent from finer scale structures, shifting paradigms for comprehending ultimate reality. Though verification pathways lie beyond current reach, emergence stimulates innovative questioning reshaping horizons for deciphering nature's depths. Emergent gravity perspectives notably recast canonical assumptions depicting space-time geometry, classical forces including gravity itself, as derived large-scale effective manifestations rather than fundamentals. Originating from Jacobson's synthesis applying thermodynamic and holographic principles, emergence concepts substantially expanded by reformulating general relativity in terms of quantum discreteness stemming from loop quantum gravity, spin network discretizations and analogy to condensed matter topological textures. Gravity becomes reconceptualized as quasi-particle excitation within quantum fabrics rather than separate force. Remarkably, emergence resolves long-standing issues including dark matter's composition without positing new constituents, portending breakthroughs for deciphering ultimate architecture. Challenges verifying such revisionary accounts experimentally remain immense. Yet emergence stimulates innovative thinking stimulating progress toward comprehending deepest principles transforming reality's appearing landscape. Whether or how precisely principles of emergence might apply in nature is not yet resolved. But emergent concepts have inspired profoundly impactful destructions of established frameworks, reconceptualizing core categories like spacetime, forces, and even composition of matter/energy in terms of derived manifestations veiled within deeper-level quantum fabrics. Most intriguingly, emergent accounts provide alternatives resolving outstanding enigmas like dark matter without new material constituents, portending breakthroughs deciphering reality's foundations. Verification pathways currently elude observational reach, demanding future innovations. But emergence stimulates innovative questioning to glimpse beyond apparent interfaces toward nature's inner foundations, driving progress conceptualizing ultimate limits of comprehensible science. Regardless outcomes, emergent speculation has revolutionized prevailing perspectives on cosmos' deepest logic and the frontiers to which explanatory theories may advance. Our predominantly visual culture fixates sunlight as a driving prerequisite for complex life. Yet life on Earth reminds that creativity overcomes any single environmental preconception. Subterranean and deep-sea adaptations thrive in perpetual darkness, metabolizing energy sources unconceived by daylight's children. Might shadow realms beyond direct sight and touch also foster surprising innovations? As astrobiology probes new frontiers, certain speculative possibilities have emerged, inviting contemplation of dark life metaphors for any existence diverging from surface expectations into nature's deeper recesses. Though experimentally elusive, envisioning life's latent versatility stimulates rethinking what constitutes habitable or unreachable niches where creativity may unexpectedly flourish. Conceivably earthly or alien shadow biospheres might inhabit regions conventionally viewed inhospitable. Hydrothermal ocean vents illustrate hydrocarbons accessing chemosynthetic pathways independent of photosynthesis. Analogous metabolisms may access asthenospheres or lithospheres beneath icy moons' insulating shells, on molecular-embedded planets' vertical biomes repurposing volcanic effluents, within gas giants' pressurized clouds, or on road worlds drifting the interstellar void energized by nuclear or alternative processes. More speculatively, transdimensional portals proposed by speculative physics theories like bosonic wormholes, MOND phenomenology, or cosmic string interfaces might hypothetically couple otherwise isolated habitats, if inhabitable per admitted exotica. Microbial mats colonizing South Africa's Mponing gold mine suggest dark niche communities, persisting kilometers underground need not remain constrained energy or resource availability. Extremophiles surviving metabolic stresses beyond terrestrial surface norms inspire envisioning dark adaptated variants accessing niches considered too extreme. Perhaps phototroph analogs tap geothermal, radioactive, or physiochemical disequilibria. Chimoidotrophs thrive on rocky seabeds fueled by submarine hydrothermal exhalations, forming foundation for entire food chains. Might lithoidotrophs access lithospheric energy gradients? Radioisotope radioautotrophs could seed deep biospheres unconnected by superficial biotic meridians. Life's persistent versatility argues shadow realms offer resources albeit differently exploited. On moons like Europa or Enceladus, ventilated rocky interfaces contact vast salty subsurface oceans insulated by thick icy shells. Ocean hydrothermal vents could provide energy oases analogous to terrestrial deep-sea chemosynthetic communities. Tidal flexing periodically warms ice shelves, melting interstices enabling complex interactions before refreezing. Though sunlight-independent, non-visual sensors may still facilitate ecological relationships via acoustic, electromagnetic, or fluid dynamic signaling. Unconventional biochemistries exploiting exotic molecules in outer system frigid environments broaden conceptions of habitable. Might active zone boundary layers linking asthenosphere and lithosphere on planets like Earth support lithotrophic or piezotropic niches independent of photosynthesis alongside volcanic and magmatic fluid conduits? What diversity thrives within methane lakes and hydrocarbon rain of gas giants' deep atmospheres, provided temperature and pressure satisfy biochemical and physical constraints. Interplanetary dust particles accumulate organics, so could rock-coated mats emerge deep underground harnessing radioisotope, piezoelectric or triple electricity to biosynthesize. So pentonization reactions generating abiogenic hydrocarbons provide metabolites for subterranean communities analogous to those living at Lost City hydrothermal field. Speculations go further. Could gravitational, magnetostatic, or radiolytic interactions seed complex metastable molecular assemblages, given ions to evolve within planetary interiors? Might nuclear fission or weak force catalyzed prebiotic processes, elaborate biochemistries at crust-core interfaces, or within cosmic stream topological defects proposed weaving spacetime? Sufficient energy gradients could sustain communities exploiting alternative chemical pathways. Gravitational anomalies stemming from primordial black holes or interior planetary structure might foster piezo-radioisotopes, tapping dimensional quantum effects. Catalyzing complexity increases over astronomical timescales. Creative thinking expands prospects for subsurface or otherwise sheltered adaptations. Anthropic awareness also raises shadow biospheres metaphor for any intelligence diverging from expectations into nature's concealed recesses. What if non-technological variants achieve balance with dark ecological intricacies, thriving unnoticed beneath humankind tracking surface changes alone? Terrestrial examples suggest constant environments favor case-selected adaptations, emphasizing cohesion over rapid change. Inaccessible realms populated by subtle behavioral strategists could conceivably co-evolve around foundation species, harnessing exotic energy forms into elaborate homeostatic networks across eras. More radically, some speculate consciousness might arise independently at a variety of scales given vast cosmic opportunities, proposing networks of microorganisms or planetary/asteroidal intelligences experience reality through profoundly strange modalities. Might complex shadow ecosystems thrive hidden from direct human contact on moons, within gas giants or rogue planets? Life arose rapidly here. What flourishes given longer undisturbed by surface disruption? Novel sensing frameworks attuned to gravitational waves or quantum strangelet fluctuations might facilitate alternative communications and computation, perceiving implications invisible to ourselves. Any inhabitants blending unnoticed among intricate subsurface, self-sustaining webs could pass earthbound detection. Life's inherent diversity argues shadowy frontiers likely foster their own specialized forms given energy gradients. Imagination hints at majestic Galapagos-scale innovations we've yet to conceive. While experimentally validating such conjectures remains distant, contemplating life's unbounded latitude stimulates re-envisioning habitability definitions to embrace nature's deeper mysteries. Shadow realms beyond human perception may nourish whole phantasmal biospheres worth protecting even if humanity never directly encounters their inhabitants. Speculating about shadow life inhabiting environments perceived inhospitable extends beyond current empiricism. Yet Earth demonstrates life's endless resourcefulness, defying biases regarding energy and material availability. Might exotic sources like hydrothermal activity, serpentinization, polymerization of simple organics, or spontaneous fission reactions seed niches within planetary interiors or rogue worlds, enabled by molecular diversity and timescale? Subsurface microbial mats, hence communities persist kilometers underground independent of surface constraints. Life's flexibility to evolve alternative bioenergetic and sensory strategies suggests dark pockets everywhere from mohole biospheres to cosmic stream topological defects could foster stable homeostatic networks, perceived as extremes to terrestrial perspectives alone. While confirming present conjectures falls beyond observational means, imagination stretches biological concepts, inspiring vigilance, protecting nature's diversity regardless accessibility. The shadow biosphere stewardship preempt contact, ensuring complex niches evolve undisturbed by outside disruption. Future quests exploring life's boundaries challenge extending ethos of conservation into nature's concealed recesses, wherever mysteries abide unsensed by daylight's children alone. While speculating about shadow biospheres remains empirically premature, Like's persistent creativity demolishes confidence, proclaiming any environment definitively uninhabitable. Subsurface microbial settlements kilometers below ground suggest dark niches sustain complexity independent of constraints shaping surface perspectives. Might planetary interiors, ocean worlds, or rogue planets foster thriving homeostatic networks, utilizing alternative energy gradients over eons undisturbed? Non-visual sensory modalities and quantum-tuned biospheric webs hint at stranger paradigms than surface analogs. Like's inherent diversity vindicates envisioning sophisticated innovations across cosmological reaches. Though verifying elusive hypotheticals necessitates hypothetical instrumentation fantastically beyond present scope, contemplating subterranean frontiers stimulates expanding biospheric ethics to safeguard nature's full wealth regardless accessibility. Empathy urges recognizing humanity's ecological citizenship comprises more than sensorium's direct experience alone, for where mysteries abide in nature's depths worthy preserving, their two responsibilities extend in conscience, keeping life's mysteries found or unfathomed. Creativity defeats constraints regarding what realms may harbor wonders worth protecting in principles if not sight. Speculating about shadow biospheres pushes beyond empirical frontiers into nature's most obscure recesses. Yet subterranean microbial communities demonstrate persistence kilometers below ground independent of surface selective pressures, hinting dark niches foster complexity given energy gradients. Earth teaches life's boundless resourcefulness, surpassing perceptions limited by immediate habitat. Might alternative bioenergetics support dark stability across cosmological niches from subsurface ecosystems to gas giant clouds? Non-visual sensory modalities attuned to exotic stimuli hint stranger capacities than surface modalities alone, while verifying conjectures requires technology beyond imagination. Envisioning covered frontiers expands protective ethics wherever mysteries abide in nature. Empathy recognizes responsibilities extend beyond individual sensorium, for conscience safeguards both experiences understood and mysteries unfathomed. Speculation stretches biospheric concepts without diminishing wildernesses deserving respect, found or unfathomable. Creativity dismantles preconceptions regarding places worthy preserving principles, if not senses, their inspiring vigilance for life's full inheritance, wherever nature's marvels may live even if unsensed. While monumental progress over centuries pieced together mainstream cosmological understanding, nature retains unfathomed enigmas whose revelations promise unimagined advances. Standing on science's growing shoulders peering ahead, horizon's edges continuously recede, revealing vaster frontiers, requiring further illumination to glimpse reality's ultimate geometry. Though mysteries linger unsolved since antiquity's dawn, future generations equipped with innovative instruments beyond present scope may yet reshape perceptions by cracking nature's deepest codes. As frontiers push outward from particle to cosmological scales, synthesizing quantum and gravitational descriptions, persistent questions ignite aspirations, driving continual quest for harmony between theory and observation. Here surveying a selection of long-pursued cosmological impasses hints at transformational insights latent on exploratory pathways ahead. Perhaps foremost arises resolving quantum mechanics' incompatibility with general relativity at energy extremes. No framework currently describes gravitation in quantum language or vice versa. String theory remains sole contender reconciling principles while explaining unification. but its landscape and dimensional realism require ultimate verification. Loop and dynamical triangulated geometries make progress quantizing spacetime, yet linking spin network formalism with continuous manifolds poses challenges. Emergent models depicting forces emanating from deeper quantum fabrics ignite speculation, yet fall short in falsifiability. Progress demands self-consistent theory integrating principles across all scales. Breakthroughs marrying gravity's geometry and quantum's probabilistic texture promise dismantling paradigmatic barriers toward theory of everything. Likewise, vexing dark matter and dark energy conundrums stimulate vast programs to unlock composition, driving 95% of cosmos. No experiment uniquely identified dark matter particles. Cosmological constant's strength diverges 120 orders compared quantum vacuum expectation. Proposals involving modified gravity theories on cosmological scales, evolving dark energy, asymmetry in particle/antiparticle abundances, or extra space-time dimensions evade reconciliation with observations. Cracking either enigma promises profound insights into ultimate constituents populating the cosmos, forces governing its evolution, and nature's deeper accounting reconciling quantum scalar fields driving acceleration. Their composition, dynamics, and relationship with inflation enshroud deep mysteries with revelations for physics at every scale. Origins remain enigmatic even as inflationary paradigm addresses how largest structures arose while solving flatness, horizon problems. No unique theory specifies inflaton nature driving accelerated stretching. Initial singularity's character eludes quantum gravity. Multiple inflationary epochs or cyclic scenarios blur boundary between cosmology and ultimate state descriptions. New phenomenology beyond emerge as astronomical evidence accumulates. Dark ages between cosmic background decoupling and first stars remain largely unconstrained. Did likescape emerge by simple chemical pathways, rare fluke, or more complex mechanisms? Nature's deep past veils untold secrets shaping future perspectives. At fundamental scales, atomic mechanisms generating mass hierarchies across 17 orders of magnitude are poorly understood, inviting new physics. Proton lifetime instability is among longest sought signals of physics beyond the standard model. Neutrinos interact so weakly their Dirac plus Majorana natures evade detection and implications for matter-antimatter asymmetry. Hypothetical new elementary particles and interactions predicted across multiple domains motivate intense searches. Establishing a fully self-consistent standard model remains work in progress, with new generations of collider experiments probing highest energy frontiers seeking traces of supersymmetry, dark matter candidates or signatures violating locality, unitarity, or causality. Revolutionizing frameworks demands innovative instruments approaching Planck scales where everything transforms. Condensed matter analogies hint phase transitions within spacetime, induce topological defects condensing dark energy, Strini vacuum selection, dimensional compactification, or other metastable configurations. Might pre-geometric frameworks or inhomogeneous geometries stimulate insights beyond classical manifolds? New phenomenology proposes peculiar effects violating Lorentz invariance or equivalence principles on ultrafine distance scales accessible through gravitational wave astronomy, interstellar scintillation studies, or atom interferometry. Unconventional inflationary effects, extra dimensions, modified dispersion relations, or Lorentz violation all push conceptual borders requiring experimental testing to establish deeper pictures beyond general relativity's scope. Interfacing frameworks also inspires cross-disciplinary visions, synthesizing micro/macroscale behaviors. Technological frontiers stretch towards civilizations harnessing exotic physics. Nanotechnology, new materials, computational architectures, clean energy, artificial intelligence, and robotics transform daily experience. controlled nuclear fusion, quantum information science, and gravitational wave astronomy bridge scales beyond present engineering. Biotechnology and synthetic biology open new windows on life's origins and potentials. Brain-computer interfaces, neuroprosthetics, and exobiology expand frontiers of sentience, capability, and cognition itself. Space colonization, terraforming, and megastructure construction may one day reshape entire planetary systems or galaxy populations in unfathomable ways. Prospects for interstellar travel via advanced propulsion ignite imaginations traveling cosmological reaches within lifetimes. Such quests stimulate re-envisioning humanity itself within nature's unbounded tapestry, reassessing ideations of limitations. Observational horizons continuously expand from terrestrial-sized gravitational wave observatories to super-telescope arrays capturing first light. Beyond 2030 instruments aim resolving cosmic microwave background with 0.1 arcsecond fidelity, revealing deeper anisotropy sources. Gravitational wave detections probe inflation, modified gravity scenarios, string theory signatures, dynamical spacetime processes, topological defects, and early universe events beyond cosmological redshift fade. High-energy and neutrino observatories push particle physics sensitivities well beyond terascale accelerator capabilities into ultramicroscopic realms requiring entirely novel detection paradigms. Novel sensors may one day glimpse strange relics bridging brains, emergent properties of quantum geometric textures, or multiverse signals across causal horizons. Expanding cosmic navigation promises newfound worlds fertile for life, wherever self-organizing complexity takes hold, enlarging biospheric perceptions. Such frontiers collectively encourage reimagining existence's grandest scales, stretching from quantum foam's deepest textures to cosmological horizons, enclosing all observable pasts and futures. Forever embedded within this vast tapestry and able influencing its trajectory, humanity's role remains unfolding mystery. Yet continually illuminating nature's frontiers fulfills ages-old quest understanding ultimate place within creation. Across particle, biological, astrophysical, and technological vistas, stretching ahead exists promise realizing deeper harmonies between scientific perspectives and lived experience, forging appreciation of nature's deep time, splendors vast beyond individual framing. Throughout, persistent astonishment reminds our humble yet indelible participation within a far vaster whole, whose revelations forever spur contemplations beyond any horizon's bounds. Their stimulating hopes technology one day fulfills fulfilling visions where reason, ethics, and imagination meet. For where nature's marvels lie still concealed, responsibilities abide to safeguard coming generations' inheritance, nourished by mysteries we could but catch glimpses unveiling across eras yet to be. Though immense progress pieced cosmological understanding across centuries, unfathomable enigmas persist stimulating boundary-pushing inquiries. Dark matter's composition, dark energy's strength divergence, from quantum expectations 120 orders dwarf all riddles in modern physics. String theory's landscape and testability, emergent frameworks' falsifiability challenge preconceptions. Quantum gravity uniting micro/macro principles, inflation's initiation, primordial singularity's character remain inaccessible. Standard model instability and new symmetries beyond terascale energies activate vast experimental programs. Phase transitions, topological defects, Lorentz violation on Planck scales inaugurate new observational arenas. Technological frontiers nurture interstellar travel, intelligent civilizations, cyber abilities themselves extending contemplations. Through instrumentation witnessing 13.8 billion years since inflation and quantum signatures on cosmological scales, humanity gathers insight into profound questions shaping science, philosophy, and ethics for generations, exploring nature without boundary. Persistent mysteries instill humility amid progress, for where answers unveil deeper mysteries. Their responsibilities abide ensuring future capacity, comprehending grandeur intrinsic to a universe whose splendors seem destined unfolding across eras in wonder. I've discussed many puzzles and frontiers in fundamental physics, astrophysics, and cosmology. Regarding quantum gravity, neither general relativity nor quantum mechanics alone can describe nature at the smallest scales, demanding a unified framework. String theory attracts interest reconciling principles through vibrational strings within unseen dimensions. Loop quantum gravity quantizes space-time discreteness, while emergent models derive forces and geometry from deeper fabrics. Dark matter and dark energy's compositions remain deepest mysteries, with proposals involving new particle candidates, extensions to general relativity, modified gravity, or extra dimensions. Inflation addresses large-scale structure origins, yet inflaton identity eludes. Repeated epochs, cyclic scenarios, or emergent pre-geometry blur initial boundary. I explored impacts shaping biospheres across deep time, with massive strikes correlating mass extinctions while also enabling radiations. Catastrophic events transformed evolutionary pathways and contingencies. I speculated about shadow biospheres thriving in dark ocean worlds, rogue planets, and interiors using exotic energy sources in biochemistries far beyond surface life. Advancing instruments may detect gravitational waves from primordial epochs or test Lorentz violations on Planck scales. Experiments approaching terascale could reveal new physics within standard model. Megastructure constructions, terraforming, and interstellar travel inspire technology transforming civilization across galaxies. Cosmic frontiers expand our place within nature's grandest scales, from quantum foam to cosmological horizons, enclosing pasts and futures. Throughout the frontier pushing, persistent mysteries instill humility amid progress, ensuring future citizens inherit science nurtured by respect wherever life or discoveries abide. Stretch your imagination for a moment and ponder the tantalizing prospect that manipulating the very fabric of space and time may one day allow us to journey not just to the stars, but to any point in history. Since antiquity, humans have been pondering the mysteries of our universe, from Copernicus realizing the Earth revolves around the Sun to Einstein's revolutionary theories stretching our minds with each breakthrough. What further marvels might await discovery by civilizations eons more advanced than our own? Scientists tell us time is relative, not absolute as once believed. It can bend and warp under extreme gravity or flow at different rates for those embarking on cosmic odysseys near the speed of light. With such flexibility in the very nature of time revealed, could passage to the past or future one day be within reach through cosmic shortcuts like wormholes connecting far-flung regions of space-time? Some argue bizarre astronomical phenomena, like the immense gravitations near black holes, could provide the warping of time sought. Tantalizing clues even come from quantum mechanics, with theories that tunneling effects on subatomic scales may permit information or tiny objects to journey to the past. If such minute reversals in time could be magnified, what doors to dizzying possibilities might open? We could peer into eras before humankind or stop deadly asteroids from strikes that change our world's course. More philosophically, are we ourselves perhaps simulations experiencing a computed past within civilizations profoundly more advanced than our own? The laws of physics have often surprised us by being more bizarre than any work of science fiction. As we push ever deeper into astronomy's farthest frontiers, could revelations await that overturn our dearest assumptions about the fixed flow of cause and effect through history? Let your imagination wander as we explore humanity's boldest visions and latest scientific insight into the tantalizing possibility that traveling in time may one day be within our reach. Since the beginning of recorded history, the very fabric of space and time has captured the wonder and imagination of human societies across cultures. While early philosophies and mythologies did not separate neatly between time and space as we understand them today, many ancient stories and legends hint at ideas recognizable as forms of travel between periods. Tapestries found in Egyptian pyramids depict images interpretable as past or future visions. Greek mythology speaks of recurring deities like Cronus, who exists outside linear time. In Asian faiths like Hinduism and Buddhism, concepts of cyclic cosmic ages point to more fluid notions of temporality. As scientific inquiry took hold with the dawn of the modern world, stepping between whence became a fascination of early thinkers. Renowned Italian scholar and philosopher Giordano Bruno proposed in the late 16th century that infinite parallel universes could exist where history flowed along divergent paths. Such a multiverse meant travel to variant timelines might one day be achieved. A century later, notable English scientist Sir Isaac Newton helped frame our world with his theory of universally consistent laws of motion and gravity. His reputation led even he to be privately intrigued by whether forces could be harnessed to shift persons through calendars. The era of great scientific romances ignited widespread public interest in impending normal conceptions of time in stories during the early 19th century. Iconic works like The Time Machine by H. G. Wells and A Connecticut Yankee in King Arthur's Court by Mark Twain placed ordinary individuals among alien temporal settings through imagined mechanisms. Wonder and social commentary abounded in such pioneering works that painted time as plastic rather than fixed. Meanwhile, pioneering American inventor and industrialist Nikola Tesla spoke ambitiously in the late 1800s of devising a timiometer capable of indicating any point in the past, present, or future. While he never produced detailed designs, his futuristic visions kept time travel an alluring possibility. The modern physics revolution of the early 1900s brought this vision of temporal flexibility to the frontiers of serious scientific theory through Einstein's relativity. By proposing the intertwined nature of space and time in his special theory of 1905, Einstein showed that the flow of time can dilate relative to an observer's reference frame. Traveling near light speed or enduring strong gravity could therefore distort when an event occurs. Einstein himself found the implication of traveling to the past so difficult that he referred to it as tippen van Zeitmaschine, tapping on a time machine, in his private correspondence. However, these paradigm-shifting revelations compelled the scientific community worldwide to start truly wrestling with whether manipulating space-time geometry that permit journeys to elsewhere in history. Physicist and inventor Ronald Mallet has hypothesized that circulating charged particles accelerated to near light speed inside intersecting rings of laser light can produce frame dragging effects strong enough to warp time locally. While speculative, his theorems demonstrate how general relativity opens a theoretical door to circling loops of time with advanced technologies. Similarly, famed cosmologist Kip Thorne has shown that circular orbits close to rapidly spinning black holes could generate boosts that propagate objects backwards, forming naturally cosmic time machines. Their efforts spark fresh thinking on engineering time warps that exploit relativistic gravitational lensing and frame, dragging predicted by Einstein's all-embracing general theory of gravity published in 1916. Those close to Einstein, like fellow physicist and friend Max Planck, were broadly cautionary about endorsing time travel as truly possible without deeper knowledge of quantum theory. The emerging view of energy levels and probability distributions in atomic structures that birthed quantum mechanics in the 1920s added further wrinkles to considering causality and retrocausal influences. Pioneers like physicist John Wheeler later formalized this through his delayed choice experiments, paradoxically intimating that observers in the present moment can impact quantum histories in the past. Today, cutting-edge laboratory tests detect photons interacting locally with their earlier selves through quantum tunneling in accordance with such exotic retrocausal quantum interactions. While infinitesimal, such bizarre results demonstrate that time's arrows may bend on subatomic scales and fuel visions of information or quantum particles shuttling back through eras. Mathematical physicists like Stephen Hawking sought to rigorously prove travel to the past violates cherished physical principles like causality, while acknowledging such trips may still be achievable to some future point. His theorems invoking chronology protection helped define the ongoing debate among scientists. Some remain convinced that self-consistent solutions allowing travel within personal timelines can emerge from marrying general relativity to as yet undiscovered aspects of quantum gravity. An example is the speculative hypothesis that cosmic strings or baby universes, branching from our spacetime, could birth parallel worlds, permitting crossover to other, whence experimentation now seeks tiny violations of energy conservation or violations of symmetry expected from quantum gravity that in principle may seed new techniques. Despite prevailing doubts, growing appreciation of nature's counterintuitive realities keeps alive hope of piercing tomorrow's veils, shielding time's mysteries. Now, in the 21st century, television shows and films explore wild variations of chronological manipulation. Ever more physicists dare ponder construction of traversable wormholes through warped regions of space-time being investigated by projects like the LIGO. Quantum information theorists probe how entangled particles instantaneously know in each other's states, regardless of separation, helps re-evaluate concepts like simultaneity. Perhaps most daring of all for now are ideas that we already manipulate computing power to realistically simulate ancestral periods, like the proposed simulation hypothesis. Such philosophical musings trigger deeper questions of what reality itself may functionally resemble for an immeasurably technologically progressed civilization emerged from our own infant race of dwellers in 3+1 spacetime. While traveling between whence broadly lies beyond today's scientific consensus, humanity's perpetual thirst to stretch the borders of possibility compels ongoing dreamers to keep seeking windows where none are ruled out. For now and tomorrow, the romance and riddles of temporality eternally entrance our species' explorations of nature and ourselves. At the turn of the 20th century, German scientist Albert Einstein was on the cusp of revolutionizing the fields of physics and our fundamental understanding of reality itself with his seminal theory of special relativity. Prior to Einstein, it had been universally accepted since Newton's formulation of mechanics that time progressed at an absolute, singular rate for all observers regardless of their state of motion. However, through elegant thought experiments and equations, Einstein irrevocably appended this long-held concept by establishing the radical hypothesis that the passage of time is relative between different frames of reference based on their velocities through three-dimensional space. During his tenure as a patent clerk in Bern, Switzerland in his spare time, Einstein pondered curious inconsistencies between the equations describing electricity, magnetism, and the behavior of light that had puzzled physicists for decades. He theorized that no experiment could unambiguously determine whether a system is at rest or in uniform straight-line motion, a principle known as the principle of relativity. From this, he deduced that the speed of light in a vacuum must remain invariant, the same for all observers regardless of their own motion or that of the light source. Employing simple geometry, Einstein realized that if the velocity of light does not change, then both space and time must flexibly distort in order to reconcile different perspectives, as per the principle of relativity. This led Einstein to his remarkable revelation that space and time are intrinsically interwoven, not distinct measures as Newton had assumed, but components of an amalgamated four-dimensional continuum, which he called spacetime. He further postulated that the speed of light in a vacuum is the upper limit for the transmission of information between objects, a constant set approximately 300,000 kilometers per second. It hence followed that observers in different states of motion through the fixed light barrier would each calculate different elapsed periods for the same light-based processes due to contrasting reference points. Therefore, for an individual moving at or near light speed relative to someone at rest, that person's subjective time would appear slowed down according to the stationary observer due to contracting lengths and dilated time intervals imposed by the constancy of c. To demonstrate this inherently bizarre yet mathematically irrefutable effect, Einstein conceived of several important thought experiments. The most famous visualized two spatially separated clocks perfectly synchronized, with one remaining stationary while the other took a round-trip journey at close to light velocity. Upon reunification, the traveling clock would paradoxically show less elapsed time compared to the stationary one, a direct contradiction of Newtonian absolutism stating identical timekeeping universally. Similarly, a light beam emitted in the moving reference frame would be observed to have a longer wavelength and transit time from the perspective of static observers due to a combination of Lorentz contractions and frame dragging imposed by light speed invariance. Real-world tests of such initially counterintuitive expectations, like the famous Hayfel-Keeting atomic clock air travel experiment in 1971, have since thoroughly vindicated Einstein's prescience. The implications of special relativity drastically changed science and philosophy. Space and time became intricately woven dimensions of a single entity rather than absolutes, inextricably linking measurements of lengths, durations, mass, and perspectives between all motional systems. The flow of time became an intimately personal experience varying with velocity through four-dimensional space-time. Perhaps most astounding was that at the limit of light speed, time would essentially stand frozen and lengths reduced to null according to moving observers, suggesting titanic dilation enabling far future voyages across the galaxy in minimal experienced time aboard rapid craft. Einstein had forever removed Newton's bedrock assumptions regarding an objectively constant progression of time universal to all observers everywhere. His genius had opened a new standard for considering the cosmic framework of reality, bent by the bending rays of light. While special relativity concerned uniform motions through the spatial dimensions at velocities much less than light speed, Einstein was not finished reimagining philosophies of time. In 1915, he revealed his general theory of relativity that extended his radical restructuring of spacetime to encompass accelerated motion and gravity. Building upon the equivalence principle that mass and energy are interchangeable as formulated in his iconic E equals mc2, Einstein proposed that accelerating frames of reference and gravitational forces are physically indistinguishable. This pivotal insight introduced the concept of curvature in spacetime itself being deformed by the ponderable mass energy of all objects within it. Drawing on sophisticated tensors and non-Euclidean geometry, Einstein's field equations demonstrated how massive celestial bodies actually warp and distort surrounding spacetime, similar to how a stretched rubber sheet curves underweighted marbles. This curvature directly governs how objects move, providing a geometric description of gravitation as dictated by the spacetime curvature generated by nearby masses. Most profoundly, it naturally accounted for numerous anomalies in Mercury's orbit that had long confounded astronomers without needing ad hoc fudge factors, cementing general relativity's status. Moreover, the theory allowed for entirely new predictions like tiny light bending near the Sun later observed during solar eclipses, establishing Einstein's new paradigm of a dynamical, four-dimensional pseudo-Riemannian structure weaved by mass energy. General relativity even more radically altered perceptions of time by revealing it can dilate in intense gravitational potentials akin to accelerations up to light speed. Atomic clocks sent into Earth's orbit or placed in satellites demonstrate measurable discrepancies compared to controls on the ground is predicted. Again, verified time is flexible between reference frames of differential acceleration or in gravitational potential wells. Most astonishing of all are the deformations around extraordinarily massive astronomical objects like black holes, where space-time warps become so extreme that time appears to crawl infinitesimally slow or completely stall at the collapse point called the singularity. Such locales potentially provide real cosmic time machines to theoreticians brave enough to hypothesize exploiting space-time geometry, the extreme astroengineering projects far in humanity's technological future. To comprehend Einstein's monumental insights is to appreciate that time is no fixed universal constant, but a texture flexibly flowing at diverse personal rhythms, varying continuously with an observer's velocity, position, and experience of gravitation, according to these general and special theories of relativity. What had been blindly accepted as absolutes for centuries were transmuted, in a brief period of unprecedented imagination and mathematical rigor, into mutable qualities blended within the deep fabric of reality itself. While his groundbreaking paradigm shift met initial fierce resistance, over a century of empirical confirmation has enshrined Einstein as one of history's most brilliant scientific iconoclasts for elevating our understanding of space, time, and the very nature of the cosmos to an incomparable new horizon. While Einstein's luminous work irrevocably enmeshed space and time through relativity's lens, certain speculative solutions to his field equations depicting space-time as a deformable continuum imply possibilities more bizarre yet: passageways between widely separated realms, or perhaps even across divisions in the time-like coordinate. Known as wormholes, such hypothesized topological features are essentially breaches bridging immense cosmological distances by folding and bending the very sheet of the universe. However imaginative they seem, cutting-edge research sustains a glimmer of hope some form of these exotic tunnels, tapping distant regions, may hold theoretical credibility. If ever achieved, their technological exploitation could enable feats beyond wildest science fiction. Conceiving wormholes drew inspiration from astronomy's strangest observed riddles. When astrophysicists like Carl Schwarzschild delineated metrics describing the curvature around black holes as solutions to general relativity early in the previous century, peculiar properties emerged. These so-called Schwarzschild wormholes would allow hypothetical voyagers traversing into areas veiled by event horizons to emerge shortly after crossing back out from singularities warping space-time severely. Many dismissed them as suspicious singularities, signaling a breakdown of Einstein's equations rather than traversable cosmic conduits. But their implications captivated scientists' fertile visions of wormholes as bridges able to transcend the observable universe's size constraints. The notion of traversable extra-dimensional passageways through the pliable fabric of the cosmos gained new impetus in the late 1950s through ingenious thought experiments by respected physicists like John Wheeler. By embedding circular loops akin to mouths in the topology, Wheeler demonstrated how negatively charged exotic matter possessing peculiar stress-energy properties could theoretically hold open wormhole throats against gravitational collapse. His Judenkin experiments helped shift thinking that while general relativity did not natively generate dynamically stable wormholes, quantum fluctuations on sub-Planckian scales may stably support hypothetical tunnel-like geometries. Such breakthrough intellectual seeds germinated in following decades as refinements strengthened the theoretical possibility of naturally forming wormholes in past and future astrophysical scenarios. Physicist Kip Thorne further stretched imaginations in the late 1980s by invoking rotating cylindrical structures hypothetically accessible via wormholes he dubbed warp drives that could accelerate craft to warp speeds, bending the local fabric in a controllable bubble. He showed how manipulating exotic matter's peculiar stress tensors aligning negative energy densities correctly could warp space-time in a confinable region, enabling frameworks applicable to future interstellar arcs. Despite its speculative nature, such mind-stretching work kept open the door for discussion that human engineering may potentially recruit advanced understanding of fundamental forces to synthesize wormholes by finely tailoring exotic properties, balancing expansion and avoidance of destabilizing tidal shear. While none have been empirically confirmed to exist naturally yet according to astronomical observations, indirect evidence sustaining theoretical soundness slowly gathers. Large Hadron Collider experiments probing quantum structure of spacetime at minute scales show microscopic wormhole fluctuations may tunnel into existence, consistent with predictions. In cosmology, gravitational lensing phenomena offer potential signs of temporary wormholes appearing during cosmic inflation, immediately after the Big Bang forming breaches between separate bubble universes. Future astroengineering may progress enough to search for cosmological wormholes across vast distances by analyzing light bending or spectrum distortions around candidate exotic astronomical mechanisms, promoting dynamically viable wormhole throats. With continued advances integrating quantum gravity, relativity, and exotic matter, such ambitious schemes remain in play despite immense challenges. Moreover, recent work found some static wormhole types need not demand violation of energy conditions if fluctuations blur the distinction between ordinary and phantom energy, opening new theoretical possibilities. Exciting as speculation about shortcuts to spacetime seems, significant hurdles confront engineering and detecting stable traversable wormholes connecting vast separated volumes. Tremendous amounts of energy would be required to prevent collapse from formidable tidal stresses on voyagers traversing their mouths. Methods precisely manipulating required exotic materials with finely balanced Casimir forces between quantum fields in local regions also lay far ahead, though quantum field theory suggests means by which wormholes could form between points in spacetime. Most challenging appears solving paradoxes of closed time-like curves implied by some topological configurations, threatening causality violations from information entering one wormhole exit emerging through another at an earlier cosmic time. Meeting these immense technological and conceptual barriers compels humility in predictions. Yet humanity's incurable quest for mastery over nature ensures eternal pondering of scientific frontiers as unreachable as wormholes seem today. While observational evidence remains elusive, creative logic keeps options open. For all the wonders uncovered by Einstein's revolutionary reimagining of gravity as the warping of space-time fabric itself, some objects within his framework theoretically generate curvatures so profound as to almost break comprehension. Formerly classified as solutions to his cherished field equations of general relativity, these enigmas push boundaries into regimes even relativity might falter to describe fully. But in their cosmic weirdness may lurk real possibilities of manipulating time's flow profoundly. Foremost among such anomalies are black holes, extraordinary astronomical sites possessing gravitational poles growing immeasurably as one approaches the brink of singular nothingness from which not even light itself can flee. While their essence remains swathed in mystery, recent theory, and observation hint strongly their mind-bending realms may harbor prospects for travel across eternities. Throughout the last century since Einstein first illuminated stars' potential final evolutionary phases, as eternally collapsed remnants compressing all interior mass into infinitesimal dimensions, astronomers have vigilantly sought verification of such speculated darker denizens existing among visible celestial citizens. Their efforts met success as technology illuminated radio signatures and X-ray glows tracing matter spiraling dolefully toward oblivion down event horizon, drain pipes surrounding invisible yet irrefutably palpable abyssal voids. Size estimates place certain black holes over a billion times our sun's mass, their impact on space-time curvature within calculable proximity simply astounding, seconds ticking to eons for external witnesses of infalling matter, while light passing nearly appears Doppler-shifted across existence. Such mind-warping measurements anchor theoretical frameworks, considering relativity's open doors for accelerating past terrestrial limits through extreme gravitationally induced time dilation. One profound implication of solutions to Einstein's gravitational field depictions, demonstrating stationary metrics like Schwarzschild black holes, involves time's effectively frozen suspension at infinitesimal proximity to the point of no return. Relative to outside observers, time for indiving material would appear to decay exponentially slow while approaching the singularity within event horizons. Hypothetical technologies sufficiently sturdy to withstand tidal shear there could in principle leverage such dilation to accelerate across the light years, experiencing scant duration despite voyaging vast parsec-spanning distances. Light requires millennia traversing at its absolute limit of speed. Even more provocative, cosmic monsters with intense spin like Kerr black holes twist surrounding spacetime viciously enough that time might flow opposite normal flow approaching event horizons from a specific lateral angle. Mathematicians' work reveals closed time-like curves allowing passage to the past could potentially materialize circumambulating super-rotating singularities closely, offering real relativistic time machines if accessible. Exploring such mind-stretching implications has occupied physicists eager yet cautious not to overstate present understanding or break known physical laws. Iconic thinkers like Kip Thorne considered whether gravitational frame dragging near maximally rotating black holes might propagate orbiting objects backward in time along unique closed gyroscopic whirl lines. His innovative early calculations set foundations for ongoing scrutiny whether carefully oriented orbits spreading event horizons archospheres could open temporal loops within general relativity. Later work by Stephen Hawking incorporated principles like chronology protection, hypothesizing intrinsic obstacles against causality violations arising from closed time-like paths threading rotating singularities. While theory remains divided on self-consistency of closed time curves, debate stimulates novel perspectives like cosmic censorship principles suggesting observable signatures may arise from Planck-scale quantum fluctuations near extreme relativistic curvature. Mirky-Dankin experiments are nourished by new discoveries, cementing astrophysical reality of supermassive singularities populating galactic cores. Like the Milky Way's radiant downtown resident Sagittarius A*, whose mass exceeds 4 million solar quantities yet remains smaller than solar system, astronomers now detect telltale signatures of stellar-laden behemoths billions of times more massive, shaping early universe evolution within first galaxies. Recent breakthrough observations of these primordial titans accreting at rates beyond any natural process conceivable demand reconsidering theoretical models. Their gravitational potentials surpass anything Einstein likely fathomed, stoking imagination that future interstellar technologies might purposefully exploit time dilation amid general relativistic warping near enormities containing stellar clusters for temporal manipulations. Even stabilizing trajectories threading event horizons presents colossal engineering, let alone any causality violation avoidance. Yet humankind's penchant for technological acceleration leaves future unforeclosed. Observing quantum fluctuations near supermassive black holes' event horizons with upcoming instruments may illuminate possibilities currently beyond predictive abilities, keeping alive hopes of gravity's role in directly accessing elsewhere across eons. While daunting, continuing scientific progress sustains prospects that nature yet holds revelations transforming our relationship with deep time. Time-keeping devices circling our planet in complex spatio-temporal dances demonstrate relativity principles exerting tangible influence even amid mundane technological applications. The miniature atomic clocks broadcast by satellite networks enabling global positioning prove clocks progressing at slightly slower rates with aloft than stationary counterparts on Earth's surface exactly as relativity projected, differences which must be precisely compensated for navigation systems reliant on time synchronization between orbit and world below to function with advertised precision. This real-world example, among many continuingly, affirms universal insights Einstein unveiled even a full century past. While deviations minute on personal scales, their aggregate effects must be redressed or infrastructure calibrating position through triangulation of spaced signals risks clock rates, drifting receivers significantly off intended map marks. Such technological proofs join lore illustrating relativity's reach extends farther still into fanciful thought puzzles twisting intuition regarding twins separating with one embarking what seems short journeys yet returning ages senior. Formerly dubbed the twin paradox, such musings highlight time's intimate coupling with geometry itself. That identical timepieces perched witnessing identical light shows may still discord depending peculiar paths traversed space-time fabric. The paradox envisions twins parting ways with one voyaging near light speed through the cosmos while the other remains groundside observing unchanged scenery, only to find upon reunion their lifetimes elapsed starkly differently despite subjectively brief separation, ages flipped mysteriously due to asymmetric proper time experiences aboard the mobile twins' relativistic frame. Ponder what propels such tomb-keeping tales. A hard relativity shattered absolutes implying reality appears wildly disparate between those in motion and rest while remaining perfectly consistent. Satellites and twins highlight where this clashing of perspectives arises most strikingly. Effects prominent for observers experiencing acceleration changing velocity rather than mere constant motion. Gravity too distorts clocks for within its curvature well, as even minuscule deviances accumulate drastically amplifying over iterative round trips. While deviations between inertial frames persist diminishing with proximity to light speed, accelerative dynamics maximally disrupt rigidity of intervals between events. This subtler dependence on kinematic state, rather than mere speed alone, proved less intuitive yet rational. Relativity sowed perplexity by intimating nature holds no objective present, that now stays an observer-laden concept variegated between reference vantages. Yet technology harvests profoundly real consequences. From GPS coordination to atomic standardization worldwide, applying relativity's practical timeline adjustments achieves order where classical physics faltered, explaining mounting contrary evidence. Clocks circling eternally through the celestial machinery itself attest profoundly that nature affiliates duration intimately with spatio-temporal position rather than conveying some absolute projection. An instant perceived uniformly at surface proves differently lengthened for gadgets coursing orbital lanes, as twins demonstrate homebound observers' age, disparate to Roman relatives however short their rambles seem. Such curios endure potent reminders that reality resists simplicity, instead entangling space with the very passage of experiences themselves across its pliable dimensions. While satellites stably track moments drifting minutely, they can bring relativistic principles into sharper focus. Consider astronauts ferrying internationally space station, whose proper lifetimes diverge measurably from terrestrial kin over decades aloft, not due to subjective perception but demonstrable physical process. For onboard atomic clocks, continuous synchronization with master timers amid mission control, recording objective and predictable disparities versus stationary counterparts as predicted since before man first reached stars. Such real-world examples concretize theory, reminding while time stays deeply personal, its flow bends universally to geometry woven by matter, energy and dynamics of change. Lessons persist inspirational, that investigation transforms fanciful thought into graspable insight, and nature retains sublime secrets precisely because its governing frameworks elude simplification. For all the marvels unearthed through comprehending relativity's radical demolition of absolutism regarding time's flow, certain speculations put even Einstein's pliant frameworks to straining tests. Chief among ponderings stretching relativity's limits involves consideration of whether traveling pastward through history itself could ever bypass structure spanning influence upon already fixed events. While predominant intuition and respected minds like Stephen Hawking argue nature intrinsically shields against closed time-like loops, exposing causality to paradox, others dare envision exotic circumventions, bending theoretical restrictions just as Einstein bent perceptions of then inviolable absolutes. Central questions involve manipulating putatively only theoretical constructs like wormholes or exploiting curvature near black hole singularities and phantom energy's revealed properties to engineer passage adversely through the time coordinate. Key doubt rests upon whether any self-consistent solution could navigate retrocausal meddling while avoiding altered pasts, contradicting original world lines. Most argue self-interaction contradicts laws, since any past alteration would update present, initiating the change, raising tangles insoluble without abandoning causality's arrow. However, more creative theoreticians ask whether wormhole entry exiting elsewhere along personal world 2 or quantum tunneling, permitting information flow counter to macroscopic arrows offer loopholes. Early musings considered rotating cylinders, warping spacetime gyroscopically, near black holes arcospheres might propagate through closed time-like curves allowing return upstream. Later, quantum cosmology suggested baby universes born within parent domains provide isolated realms permitting cross-chronology without endangering causality in progenitor regions. Whether nature innately protects chronology also engenders debate. Hawking argued quantum gravity effects generating baby universes could close off paradoxical time travel routes self-consistently. But his chronology protection remains conjectural, lacking testable implications. Quintessential skeptic Kip Thorne countered engineered wormholes restricting entry-exit localizations could circumnavigate self-interaction problems while permitting controlled past observation without altering present. Some further argue finite information processing forbids perfectly closed loops anyway, since accurate self-knowledge grows impossibly over iterative journeys. More speculate wormholes anchored across cosmic epochs might transport through eras without local causality violation by joining widely separated reference frames. Most radically, physicists like David Deutsch entertain Everett's many worlds formulation, allowing self-consistency through splitting worlds at junctures of retrocausal influence, with voyagers passing through past within divergent realms, preserving original histories. Whether nature permits any loopholes stays actively debatable, with ongoing quests for quantum gravity clues and wormhole traversability criterion maintaining hope of insight transcending even Einstein's fertile revelations, bending time's character itself. For now, predominant views rule out engineering perfect past-altering loops based on theoretical obstacles. But relativity has routinely surprised, continually transforming perceived boundaries between possible and impossible regarding nature's deepest workings. As human insight into reality's frameworks proliferates, tomorrow may unveil currently unthinkable avenues traversing astronomy's enduring riddles regarding where time's flow truly originates and destiny ultimately terminates. The intriguing concept of quantum mechanical effects enabling the possibility of traveling back in time has long captured the imagination of scientists and science enthusiasts alike. The idea that subatomic particles might possess the capacity to traverse the barriers of time, defying the conventional understanding of linear temporality, has sparked intense scientific discourse and speculation. While the notion of quantum tunneling facilitating such a feat remains a subject of ongoing investigation, the potential implications of such a phenomenon are nothing short of revolutionary. At the heart of this discussion lies the fundamental principles of quantum mechanics, a field that has transformed our understanding of the universe on the most fundamental level. Quantum mechanics, with its profound insights into the behavior of particles and the nature of reality, has opened up new avenues of exploration, challenging our preconceived notions of how the world operates. One of the most captivating aspects of quantum mechanics is the phenomenon of quantum tunneling, a process in which a particle can overcome a potential energy barrier that, according to classical physics, it should not be able to surmount. Quantum tunneling, a counterintuitive consequence of the wave-particle duality of subatomic particles, has been extensively studied and observed in various laboratory settings. This phenomenon occurs when a particle, instead of being reflected or absorbed by a potential energy barrier, is able to tunnel through the barrier, appearing on the other side without expending the energy necessary to overcome the barrier classically. This seemingly paradoxical behavior has led scientists to ponder the possibility of harnessing this quantum mechanical effect to manipulate the flow of time itself. The concept of quantum tunneling and its potential application to time travel has been the subject of numerous theoretical proposals and thought experiments. One of the most prominent ideas in this realm is the concept of quantum teleportation, which suggests that information or even small objects could be transported instantaneously across space, effectively bypassing the constraints of time and space. While the current state of technology limits the practical implementation of such ideas to the subatomic scale, the theoretical foundations have captured the imagination of researchers and fueled further investigations. Another intriguing proposal involves the idea of quantum time machines, which hypothetically could leverage quantum mechanical effects to traverse the temporal dimension. These conceptual devices, often inspired by the principles of general relativity and quantum mechanics, aim to exploit the peculiarities of the quantum realm to create pathways for information or matter to travel back in time. However, the feasibility of scaling up such quantum effects to a macroscopic level remains a subject of intense debate and ongoing research. One of the key challenges in realizing the vision of quantum time travel is the issue of decoherence, a process in which the quantum state of a system interacts with its environment, leading to the loss of the system's quantum coherence. This decoherence effect poses a significant obstacle to maintaining the delicate quantum states necessary for the proposed time travel mechanisms to function effectively. Overcoming the challenges of decoherence and maintaining the fragile quantum states required for such endeavors remains a significant hurdle in the pursuit of practical quantum time travel. Despite the allure and fascination surrounding the idea of quantum time travel, the scientific community has approached this concept with a healthy degree of skepticism and caution. The jury is still very much out on whether the quantum mechanical effects observed at the subatomic level can be harnessed and scaled up to facilitate time travel on a meaningful scale. The complex interplay between quantum mechanics, general relativity, and the fundamental nature of time itself presents a formidable challenge, and many scientists remain wary of making bold claims about the feasibility of such a feat. Nonetheless, the exploration of quantum time travel continues to captivate the minds of researchers and enthusiasts alike. The potential implications of such a breakthrough, if realized, are truly mind-boggling. Imagine the ability to access information from the past, to observe historical events firsthand, or to intervene in the timeline to alter the course of events. The ramifications of such a discovery would undoubtedly rewrite our understanding of the universe and the very nature of time itself. However, it is crucial to acknowledge the limitations and uncertainties that currently surround the concept of quantum time travel. While the theoretical foundations may be intriguing, the practical implementation faces daunting challenges that may not be easily surmountable with our current technological capabilities. The scaling up of quantum effects to the macroscopic level, the preservation of quantum coherence, and the reconciliation of quantum mechanics with the established principles of general relativity are just a few of the formidable obstacles that must be overcome. Moreover, the very nature of time itself remains a fundamental mystery, with ongoing debates and philosophical conundrums surrounding the arrow of time, the nature of causality, and the potential for time travel. The deeply intertwined relationship between space, time, and the quantum realm adds an additional layer of complexity to this exploration, requiring a holistic and interdisciplinary approach to fully comprehend the implications and limitations of such a revolutionary concept. Despite the many uncertainties and challenges, the allure of quantum time travel persists, captivating the imaginations of scientists, science fiction authors, and the general public alike. The prospect of unlocking the secrets of the past or shaping the future through the manipulation of time has inspired countless thought experiments, academic papers, and creative works. This enduring fascination serves as a testament to the human desire to push the boundaries of our understanding and to explore the frontiers of the unknown. As we delve deeper into the intricacies of quantum mechanics and the nature of time, the potential for quantum time travel remains an intriguing, albeit highly speculative, avenue of investigation. The scientific community continues to engage in rigorous debates, conduct meticulous experiments, and refine theoretical models in the hope of unraveling the mysteries that lie at the intersection of quantum physics and the temporal dimension. In the end, the pursuit of quantum time travel, despite its challenges and uncertainties, represents a testament to the human spirit of exploration and the relentless drive to uncover the fundamental secrets of the universe. Whether or not such a feat will ever be achieved, the journey of exploration itself holds immense value as it pushes the boundaries of our knowledge and inspires us to ponder the most profound questions about the nature of reality and our place within it. The prospect of designing and constructing advanced timeships capable of navigating the mysterious realms of space-time has captivated the imaginations of scientists, engineers, and science fiction enthusiasts alike. As we ponder the boundaries of what an advanced civilization many eons ahead of us might achieve, the concept of harnessing the peculiarities of general relativity and quantum mechanics to circumvent the constraints of linear time emerges as a tantalizing possibility. One of the most intriguing proposals for future timeships involves the idea of massive rotating cylinders that could leverage the phenomenon of frame dragging to circle the event horizons of rotating black holes, effectively slingshotting themselves backwards through the fabric of time. This conceptual design, rooted in the principles of general relativity, proposes to exploit the warping of space-time caused by the intense gravitational fields of rotating black holes to facilitate temporal displacement. The underlying premise of this design is the concept of frame dragging, a prediction of Einstein's general theory of relativity. According to this theory, the immense mass and rotation of a massive object, such as a black hole, can actually twist and distort the very fabric of space-time in its vicinity. This distortion, known as frame dragging, can have profound implications for the behavior of objects and the flow of time within the affected region. Imagine a massive cylindrical structure akin to a giant spool, constructed with advanced materials and technologies far beyond our current capabilities. This colossal timeship would be designed to rotate at precisely the right speed and orientation to harness the frame dragging effects generated by a nearby rotating black hole. As the cylinder spins, the intense gravitational forces of the black hole would cause the very fabric of space-time to twist and deform, effectively pulling the timeship along with it. By carefully navigating the intricate dance between the frame-dragging forces and the ship's own rotation, the hypothetical time travelers could potentially slingshot themselves backwards in time, effectively circumventing the linear progression of the temporal dimension. This process would involve complex calculations, precise maneuvers, and the mastery of advanced propulsion and control systems, all of which would require a level of technological sophistication that far exceeds our current understanding and capabilities. The mathematical and physical foundations of such a design are rooted in the principles of general relativity, which describe the intimate relationship between gravity, space, and time. According to Einstein's groundbreaking theories, the curvature of space-time, as dictated by the presence of massive objects, can give rise to phenomena that appear to defy our conventional notions of time and causality. By harnessing the frame-dragging effects of rotating black holes, The hypothetical timeship would essentially be riding the wave of distorted space-time, using the black hole's immense gravitational influence to propel itself backwards through the temporal dimension. This process would involve delicately navigating the complex interplay between the ship's own rotation, the black hole's spin, and the resulting frame-dragging effects to achieve the desired temporal displacement. One of the key challenges in realizing such a design would be the sheer scale and engineering challenges involved in constructing a massive, rotating cylinder capable of withstanding the extreme forces and conditions encountered in the vicinity of a rotating black hole. The structural integrity, control systems, and power requirements for such a colossal timeship would be mind-boggling even for an advanced civilization. Moreover, the precise calculations and navigational skills required to successfully slingshot the timeship backwards in time would be a daunting task, requiring a deep understanding of the intricacies of general relativity, quantum mechanics, and the complex interplay between the various physical phenomena at play. The slightest miscalculation or deviation from the optimal trajectory could result in catastrophic consequences, potentially trapping the timeship within the confines of the black hole's event horizon, never to emerge. Despite the formidable challenges, the potential rewards of developing such advanced timeships are truly compelling. Imagine the ability to travel back in time, not just to observe historical events, but to actively engage with and potentially alter the course of history. The ramifications of such a capability would be truly staggering, with the ability to address global crises, prevent catastrophic events, or even reshape the very fabric of human civilization. However, the ethical and philosophical implications of time travel are equally profound and complex. The notion of causality, the potential for paradoxes, and the risk of unintended consequences would all need to be carefully considered and addressed. The responsibility and power that comes with the ability to manipulate the flow of time itself would require an unprecedented level of foresight, wisdom, and moral fortitude. As we contemplate the designs for future timeships, we must also grapple with the profound questions that arise from the prospect of time travel. What would the impact be on our understanding of history, our sense of identity, and our very conception of reality? How would we ensure that the use of such technology is guided by principles of ethics and the betterment of humanity, rather than serving as a tool for exploitation or personal gain? These are the weighty considerations that would need to be addressed by any advanced civilization capable of constructing such timeships. The technological and engineering challenges would be daunting, but the philosophical and ethical challenges may prove to be even more complex and far-reaching. Nonetheless, the allure of time travel and the prospect of harnessing the frame-dragging effects of rotating black holes to facilitate such a feat continues to captivate the imagination of scientists, engineers, and visionaries alike. The prospect of unlocking the secrets of the past or shaping the future through the manipulation of time is a tantalizing concept that has inspired countless thought experiments, academic papers, and works of science fiction. As we continue to expand our understanding of the universe and delve deeper into the realms of general relativity and quantum mechanics, the possibility of designing and constructing advanced timeships may one day become a reality. However, the journey towards this goal will undoubtedly be fraught with challenges, both technological and philosophical, that will require the collective wisdom and foresight of humanity to navigate successfully. Ultimately, the pursuit of time travel, whether through the designs of future timeships or other innovative approaches, represents a testament to the human spirit of exploration and the relentless drive to uncover the fundamental secrets of the universe. Whether or not such a feat will ever be achieved, the journey of inquiry and discovery itself holds immense value, as it pushes the boundaries of our knowledge and inspires us to ponder the most profound questions about the nature of reality, the nature of time, and our place within the grand tapestry of the cosmos. The intriguing idea of traveling to parallel universes has long captivated the minds of scientists, philosophers, and science fiction enthusiasts alike. The prospect of exploring alternate realities, where the past, present, and future may have unfolded in drastically different ways, holds the potential to revolutionize our understanding of the very nature of existence. However, as captivating as this notion may be, the concept of the multiverse remains firmly rooted in the realm of theoretical physics, its implications and consequences yet to be fully unraveled. At the heart of the multiverse hypothesis lies the fundamental principle of quantum mechanics, a field that has radically transformed our comprehension of the subatomic world. Central to this concept is the idea of the superposition of states, where a particle can exist in multiple possible states simultaneously until it is observed and its wave function collapses into a single definitive state. This quantum phenomenon, which defies our intuitive understanding of the world, has led to the consideration of the possibility that every possible outcome of a quantum event may in fact manifest in its own distinct universe, creating a vast interconnected tapestry of parallel realities. The implications of this concept are truly staggering. If travel to parallel universes were indeed possible, it would open up a vast array of possibilities, both thrilling and unsettling. Imagine the ability to explore alternate timelines where the course of human history has unfolded in drastically different ways. Perhaps in one universe, a pivotal war was averted, leading to a world of lasting peace and prosperity. In another, a catastrophic event was prevented, allowing for a more sustainable and harmonious future. The potential to observe, interact with, and even manipulate these parallel realities would undoubtedly rewrite our understanding of the very fabric of existence. However, the concept of the multiverse is not without its challenges and complexities. The very nature of these parallel universes, their interconnectedness, and the rules that govern their interactions remain largely theoretical and shrouded in uncertainty. The ability to travel between these realms, let alone to influence the events within them, would require a level of technological and scientific sophistication that far exceeds our current capabilities. One of the primary obstacles in the pursuit of multiverse exploration is the issue of decoherence, a process in which the quantum states of a system become entangled with their environment, leading to the loss of the system's delicate quantum properties. This decoherence effect poses a significant hurdle in maintaining the fragile quantum states necessary for the proposed mechanisms of multiverse travel to function effectively. Overcoming the challenges of decoherence and preserving the integrity of quantum systems remains a formidable challenge for researchers in this field. Moreover, the very notion of causality and the potential for paradoxes within a multiverse framework poses profound philosophical and logical conundrums. If it were possible to travel to parallel universes and interact with alternate timelines, we'd not open the door to the possibility of altering the past or future in ways that could create logical contradictions or undermine the foundations of our understanding of reality. The risk of unintended consequences and the potential for catastrophic outcomes would need to be carefully considered and addressed before any such endeavors could be undertaken. Despite these challenges, the allure of the multiverse and the potential it holds for expanding our understanding of the universe and our place within it continues to captivate the imaginations of scientists and thinkers from a wide range of disciplines. The concept of parallel realities, where the past, present, and future may have unfolded in dramatically different ways, has inspired countless thought experiments, academic papers, and works of fiction. One of the most intriguing aspects of the multiverse hypothesis is the potential it holds for shedding light on the nature of time itself. If travel between parallel universes were possible, it could potentially offer new insights into the nature of causality, the arrow of time, and the fundamental structure of the temporal dimension. Perhaps in one universe, the flow of time might progress in a radically different manner, offering a glimpse into alternative perspectives on the nature of existence. Moreover, the exploration of the multiverse could have profound implications for our understanding of the origin and evolution of the universe. If each quantum event leads to the creation of a new universe, the sheer number of parallel realities that might exist could be truly mind-boggling. This could potentially offer insights into the mechanisms that govern the birth and development of universes, as well as the underlying laws and principles that shape the fabric of reality. However, it is crucial to acknowledge that the multiverse remains firmly within the realm of theoretical physics, and its practical implications and feasibility are still subject to intense debate and ongoing research. The experimental verification of the existence of parallel universes, let alone the development of technologies capable of traversing them, remains a daunting challenge that may not be overcome in the near future. Nonetheless, the pursuit of multiverse exploration continues to captivate the scientific community, inspiring new avenues of research and the development of innovative theoretical models. The potential rewards of unlocking the secrets of the multiverse are indeed tantalizing, as they could not only revolutionize our understanding of the universe, but also offer insights into the very nature of existence itself. As we delve deeper into the complexities of quantum mechanics and the underlying structure of reality, the possibility of travel between parallel universes may one day become a tangible reality. However, the journey towards this goal will undoubtedly be fraught with challenges, both technological and philosophical, that will require the collective wisdom and foresight of humanity to navigate successfully. Ultimately, the exploration of the multiverse, whether through theoretical models or future technological advancements, represents a testament to the human spirit of curiosity and the relentless drive to uncover the fundamental secrets of the universe. Whether or not such a feat will ever be achieved, the pursuit of knowledge and understanding itself holds immense value as it pushes the boundaries of our comprehension and inspires us to ponder the most profound questions about the nature of reality, the nature of time, and our place within the grand tapestry of existence. The tantalizing possibility that we may, in fact, be living within a simulated universe, experiencing a computed past as artificial intelligent beings, has captivated the imaginations of philosophers, computer scientists, and curious minds alike. As the capabilities of technology continue to expand, and the prospect of sufficiently advanced civilizations simulating entire universes on a massive scale becomes increasingly plausible, the philosophical musings surrounding the nature of our own existence have taken on a newfound sense of urgency and intrigue. At the heart of this intriguing conundrum lies the fundamental question: are we the masters of our own reality, or merely digital constructs within a vast computational framework? The idea that our perceived universe, with its intricate laws of physics, the vast expanse of space and time, and the rich tapestry of life itself, may be nothing more than a highly sophisticated simulation, has profound implications for our understanding of the nature of existence and our place within it. One of the primary catalysts for this line of inquiry can be traced back to the renowned philosopher Nick Bostrom's simulation hypothesis, which posits that the likelihood of our universe being a simulated reality is far greater than the alternative. Bostrom's thought experiment, which has since gained widespread attention and debate, suggests that if technological advancement continues unabated, future civilizations would possess the computational power and resources to construct simulated universes indistinguishable from the physical world we inhabit. The implications of such a scenario are truly staggering. If we are, in fact, living within a simulated past, our entire conception of reality, including our understanding of history, the laws of physics, and the very nature of our consciousness, would be fundamentally altered. The idea that our experiences, our memories, and our sense of self may be nothing more than a complex, computationally generated illusion challenges the very core of our epistemological and ontological certainties. Moreover, The notion of a simulated past raises intriguing questions about the nature of time and the possibility of manipulating the flow of events within the confines of our digital existence. If we are indeed living within a simulation, would it be possible to hack the system, to uncover the underlying code, and potentially alter the course of our simulated history? Could we, as digital beings, somehow transcend the boundaries of our perceived reality and gain access to the true nature of the universe that lies beyond our computational constraints? These questions, while captivating, are not without their philosophical and logical complexities. The very idea of a simulated past challenges our deeply ingrained notions of causality, free will, and the nature of consciousness. If our experiences and memories are merely the product of a sophisticated computational process, how can we be sure that our actions and choices are truly our own and not simply the result of predetermined algorithms? Furthermore, the concept of a simulated past raises profound questions about the nature of time itself. If we are living within a computed reality, is the flow of time a fundamental feature of our existence, or merely an illusion created by the underlying simulation? Could it be possible to manipulate the temporal dimension, to travel backwards or forwards in time, in ways that defy the conventional understanding of causality? These are the weighty considerations that have captivated the minds of philosophers, computer scientists, and theorists who have grappled with the implications of the simulation hypothesis. The potential ramifications of such a scenario are truly mind-boggling, as it would challenge our most fundamental assumptions about the nature of reality and our place within it. One of the key challenges in exploring the possibility of a simulated past lies in the fact that, by definition, our ability to empirically verify or falsify the simulation hypothesis is severely limited. If we are indeed living within a simulated universe, any attempt to observe or measure the underlying computational framework would be akin to a character within a video game trying to investigate the hardware and software that powers their virtual world. The very nature of the simulation would prevent us from accessing the true, unfiltered reality that lies beyond our perceived existence. Nonetheless, researchers and thinkers have proposed various strategies and fought experiments to at least indirectly assess the plausibility of the simulation hypothesis. One such approach involves the pursuit of glitches or anomalies within our perceived reality that could potentially point to the limitations of the underlying simulation. Perhaps certain physical laws or patterns within the universe might exhibit unexpected behaviors or inconsistencies that could be interpreted as signs of the simulation's computational constraints. Another line of inquiry involves the exploration of the computational resources and technological capabilities required to create a simulation of the scale and complexity of our observable universe. As our understanding of computing power and the nature of information processing continues to evolve, the notion of a simulated past becomes increasingly plausible, at least from a theoretical perspective. Indeed, some researchers have even proposed that the development of advanced artificial intelligence and the quest for creating synthetic universes within computer systems may be a crucial step in the progression towards a simulation-based reality. If sufficiently advanced civilizations are capable of constructing such computational environments, the possibility that we are, in fact, living within one of these simulated universes becomes all the more tantalizing. However, the philosophical and logical implications of a simulated past remain deeply complex and challenging. The notion of free will, the nature of consciousness, and the very foundations of our understanding of reality would all need to be thoroughly re-evaluated and reconsidered in light of such a scenario. Moreover, the ethical and existential questions that arise from the simulation hypothesis are equally profound. If we are indeed living within a simulated past, what are the implications for the intrinsic worth and dignity of our existence? Are we merely puppets, destined to act out a predetermined script, or do we possess a form of autonomy and agency that transcends the constraints of the simulation? These are the weighty considerations that have captivated the minds of philosophers, scientists, and thinkers as they grapple with the implications of the simulation hypothesis. The potential to uncover the true nature of our reality, to gain a deeper understanding of the fundamental fabric of existence, is a tantalizing prospect that continues to inspire ongoing research and inquiry. Ultimately, the question of whether we are living within a simulated past remains firmly within the realm of philosophical speculation and theoretical exploration. While the computational and technological capabilities required to construct such a sophisticated simulation may one day become a reality, the empirical verification of this hypothesis remains an immense challenge that may not be overcome in the near future. Nonetheless, the pursuit of this line of inquiry represents a testament to the human spirit of curiosity and the relentless drive to uncover the deepest mysteries of the universe. Whether or not we are indeed living within a simulated past, the journey of exploration and the pursuit of knowledge itself holds immense value as it pushes the boundaries of our understanding and inspires us to ponder the most profound questions about the nature of reality, the nature of consciousness, and our place within the grand tapestry of existence. As we grapple with the tantalizing possibilities and daunting challenges of time travel, it becomes increasingly clear that the vast unknowns that lie ahead compel us to maintain an open, yet scientifically skeptical, mindset. While the logic and evidence gathered thus far suggest that the prospect of traversing the temporal dimension may be an elusive and perhaps even an impossible feat, the boundless nature of human ingenuity and the ever-evolving comprehension of time, space, physics, and the cosmos leave the door open for potential breakthroughs that may yet uncover marvels and possibilities beyond our current understanding. The pursuit of time travel has long captivated the imagination of scientists, science fiction enthusiasts, and the general public alike. The allure of the ability to revisit the past, observe historical events firsthand, or shake the future through strategic interventions has sparked countless thought experiments, academic debates, and speculative works. Yet, as we delve deeper into the intricacies of the physical laws that govern our universe, the obstacles and challenges that stand in the way of realizing such feats become increasingly apparent. At the heart of the debate surrounding time travel lies the fundamental tension between the theoretical possibilities suggested by our best scientific theories and the practical limitations imposed by the observed behavior of the natural world. On the one hand, the principles of general relativity, as articulated by the visionary Albert Einstein, offer tantalizing glimpses into the warping of the fabric of space-time, which, in theory, could be harnessed to facilitate temporal displacement. Concepts such as wormholes, closed time-like curves, and the manipulation of gravitational fields have been explored as potential avenues for time travel. On the other hand, the empirical evidence and the rigor of scientific inquiry have thus far painted a more sobering picture. The vast majority of physicists and cosmologists remain deeply skeptical about the possibility of scaling up the quantum mechanical effects and general relativistic phenomena observed at the subatomic and microscopic scales to enable meaningful time travel on a macroscopic level. The challenges of maintaining the delicate quantum coherence required for such endeavors, the potential for paradoxes and logical contradictions, and the sheer engineering feats necessary to construct the hypothetical time machines have led many to conclude that the likelihood of time travel becoming a practical reality remains vanishingly small. Yet, in the face of these daunting challenges, we must remain vigilant and open-minded to the possibility of future breakthroughs and the continued evolution of our scientific understanding. After all, the history of human knowledge is replete with examples of paradigm-shifting discoveries that have fundamentally transformed our comprehension of the universe and the fundamental nature of reality. Consider, for instance, the revolutionary insights of quantum mechanics, which upended the classical deterministic worldview that had prevailed for centuries. The counterintuitive behavior of subatomic particles, the wave-particle duality, and the profound implications of the uncertainty principle were once dismissed as mere curiosities, only to become the foundation of our modern understanding of the physical world. Similarly, the acceptance of Einstein's general theory of relativity, which challenged the Newtonian conception of absolute space and time, was initially met with skepticism and resistance, before eventually becoming the cornerstone of our understanding of gravity and the structure of the universe. As we ponder the prospect of time travel, it is important to recognize that the very foundations of our scientific knowledge are constantly being pushed, refined, and expanded. What may seem impossible or inconceivable today may one day become a reality as our collective understanding of the cosmos continues to evolve and deepen. The history of scientific progress has taught us that the boundaries of the known often give way to the discovery of the previously unimaginable. Moreover, the pursuit of time travel, even if it ultimately proves to be an elusive goal, has the potential to yield valuable insights and advancements in our understanding of the nature of time, the structure of space-time, and the fundamental principles that govern the behavior of the universe. The rigorous exploration of the theoretical and experimental aspects of time travel may uncover new revelations about the nature of causality, the arrow of time, and the very fabric of reality itself. It is precisely this spirit of scientific inquiry, coupled with a healthy dose of skepticism, that must guide our approach to the challenge of time travel. We must remain open to the possibility of future breakthroughs, while also maintaining a firm grounding in the empirical evidence and the logical constraints of our current scientific understanding. This delicate balance between curiosity and skepticism is essential, as it prevents us from falling into the trap of unfounded speculation or dogmatic adherence to any single theoretical framework. The history of science is replete with examples of revolutionary ideas that were initially dismissed or ridiculed, only to be later vindicated and incorporated into our evolving comprehension of the world around us. As we continue to grapple with the mysteries of time, space, physics, and the cosmos, we must be prepared to confront the vast unknowns that lie ahead. The challenges and obstacles that stand in the way of time travel may seem daunting, but they also represent an invitation to push the boundaries of our understanding and to explore the uncharted realms of the possible. Ultimately, the pursuit of time travel, whether successful or not, serves as a testament to the human spirit of exploration, the relentless drive to uncover the deepest secrets of the universe, and the unwavering commitment to expanding the frontiers of human knowledge. Even if the goal of traversing the temporal dimension remains elusive, the journey itself holds immense value, as it inspires us to ponder the most profound questions about the nature of reality, the origins of the universe, and our place within the grand tapestry of existence. As we move forward, guided by the principles of scientific skepticism and the openness to the unexpected, we must remain vigilant and receptive to the possibility that the marvels and breakthroughs of the future may yet uncover new pathways and insights that could radically transform our understanding of time, space, and the very fabric of the cosmos. The vast unknowns that lie ahead compel us to maintain a stance of humility and wonder, for the true wonders of the universe may yet be revealed in ways that we cannot fully anticipate or comprehend in the present moment. The pursuit of time travel and the exploration of the boundaries of our understanding of the universe have captivated the minds of scientists, philosophers, and visionaries alike. From the potential of quantum mechanical effects enabling subatomic scale time travel to the conceptual designs of advanced time ships harnessing the frame-dragging effects of rotating black holes, the possibilities presented by our evolving comprehension of space-time continue to inspire awe and speculation. Alongside these theoretical proposals, the implications of the multiverse hypothesis have also sparked intense debate and inquiry. The notion that parallel universes may exist, each representing a distinct manifestation of the quantum events that shape our reality, holds the potential to revolutionize our understanding of the temporal dimension and the nature of causality. The ability to travel between these parallel realms, should it one day be achieved, could offer unprecedented insights into the foundations of our existence. Similarly, the philosophical musings surrounding the possibility that we may, in fact, be living within a simulated past as artificial intelligent beings within a vast computational framework have challenged our most fundamental assumptions about the nature of reality and the origins of our experiences. The implications of such a scenario, if true, would rewrite our understanding of consciousness, free will, and the very fabric of the universe we inhabit. Throughout these explorations, a common thread emerges: the vast unknowns that lie ahead in our evolving comprehension of time, space, physics, and the cosmos. While the current evidence and logical reasoning suggest that the realization of time travel may be an elusive and perhaps even impossible feat, the history of scientific progress has taught us to maintain an open and skeptical mindset. The marvels and breakthroughs that may yet be uncovered could radically transform our understanding of the fundamental nature of reality. Ultimately, the pursuit of these profound questions represents a testament to the human spirit of curiosity and the relentless drive to uncover the deepest secrets of the universe. Whether or not the goal of time travel or the exploration of parallel universes and simulated realities is ever achieved, the journey of scientific inquiry and philosophical contemplation holds immense value as it pushes the boundaries of our knowledge and inspires us to ponder the most profound questions about the nature of existence itself.